The Big Bang wasn't a beginning. It was an eraser, scrubbing the universe so clean we weren't supposed to find fingerprints underneath. But the cosmos doesn't look blank. It looks like it remembers. Patterns in the sky, impossible smoothness, whispers in the oldest light. So what if before isn't a time at all? And what terrifying thing did our universe survive to get here? There is a limit to what the human mind can picture, and cosmology has learned to aim directly at it. What we call the beginning may be only the first scene we can reconstruct, not the first scene that occurred. The question is not merely what preceded a cosmic fireball, but whether precedence itself survives at extreme scales. Physics can draw a straight line from today's galaxies back to a fraction of a second. Then the line hits a seam, and our language goes thin. In that seam, cause and effect can trade places, and nothing can become a technical word with sharp edges. This documentary follows 7 theories that try to cross that seam without pretending it is easy. Some begin with a prior cosmos fading into ours, leaving only subtle debts in the oldest signals we can measure. Others begin with emptiness, not as philosophy, but as a quantum state that refuses to stay empty. Some treat our universe as one event in an endless production line, where creation is common and meaning is scarce. One turns the Big Bang into aftermath, an impact between vast domains, where a collision can look like a birth from the inside. So we begin at the boundary where our best models hesitate, and we push, carefully, into what they permit. If the universe truly has no before, then the question changes us more than it changes the cosmos. And if there was something, anything, then whatever it was did not merely precede our universe. It defined the rules by which universes can begin. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we move from dying predecessor worlds to quantum emptiness, multiverse machinery, brain impacts, timeless cosmologies, block time, and pure mathematics. Each step tightens the same question, until before becomes either a discoverable structure or a word that finally breaks. The Big Bang sits in our textbooks like a first page, but our equations treat it like a wall. When we run the cosmic story backward, the math does not reveal a clean origin. It reveals a boundary where our best descriptions stop working, as if the universe turns into a question mark. That boundary matters because it shapes what we think existence is allowed to do. If the Big Bang is only the edge of reliable physics, then beginning becomes a claim, not a measurement. The central question returns with sharper teeth, because language itself starts to wobble. Did anything exist before the Big Bang? And if time began there, what could before even mean? Cosmology is not built on pure speculation, so we start with anchors that can be checked. The cosmic microwave background is the universe's afterglow, released when atoms first formed and light finally traveled freely. In visual terms, it is a faint, nearly uniform glow across the whole sky, microwaves stretched by expansion into a cold bath. Large-scale structure maps how matter clumped into galaxies and voids over billions of years, tracing a cosmic web of filaments and empty bubbles. Primordial element abundances, predicted by Big Bang nucleosynthesis, record the first minutes when protons and neutrons assembled into helium and traces of lithium. Each pillar is a different kind of evidence, and they converge on the same early conditions. The CMB tells us the universe was once hot enough to keep electrons and nuclei apart, forming a plasma that scattered light. When the cosmos cooled to roughly a few thousand Kelvin, electrons settled into atoms, and photons decoupled, free at last. Those photons have been traveling ever since, their wavelengths stretched by the expansion into the microwave band we detect today. Large-scale structure adds a slower, heavier record because gravity amplifies small density differences into clusters and superclusters. The element abundances add a clock because nuclear reaction rates depend sensitively on temperature and density. These three pillars tell a consistent story of a hot, dense, early phase. They do not directly show a first moment, only an early one that is already underway. They also hint that the universe began in an unusually smooth state, with tiny fluctuations that later grew. That smoothness is part of the unease, because it looks tuned for a long future. In the CMB, the temperature varies by only tens of microkelvin across the sky, a whisper of difference on top of near-perfect uniformity. As a visual, imagine the CMB map as a mottled sphere, like a softly speckled eggshell. Those speckles are not noise in the ordinary sense, because they encode primordial density variations. They are the seeds of everything that later becomes dramatic: galaxies, stars, and the chemistry of life. Yet the overall uniformity is so striking that it raises a deeper puzzle. Why should regions of space that appear causally disconnected look so similar in temperature and density? When we push general relativity all the way back, it predicts a singularity at t=0. Density and curvature shoot to infinity, and the equations lose predictive power. In practice, the curvature scalars that describe spacetime's bending diverge, and the notion of a smooth geometry collapses. A singularity is not a place we can visit with instruments, or even with consistent mathematics. It is a warning light that the theory is being asked to do something it cannot. Historically, this was not just a philosophical discomfort, because it emerged from the same equations that correctly predicted black holes and gravitational waves. The Hawking-Penrose singularity theorems sharpened the problem, showing that under broad conditions, singularities are not rare quirks. They are generic outcomes of gravitational collapse, and in standard cosmology, of extrapolating expansion backward. That does not prove the universe began at a singular point, because the theorems assume classical spacetime. They show, instead, that classical spacetime cannot be the whole story. So the Big Bang, in this view, is not a proven birth event. It is the point where a successful theory breaks, and where new physics must take over, quietly but decisively. The terrifying possibility is simple, and it changes the emotional temperature of the question. If the breakdown is only a limit of our model, then the universe might extend past it. One family of ideas answers by refusing a true beginning, while keeping the early hot phase we observe. Cyclic cosmologies imagine a universe that expands, then contracts, then rebounds into another expansion. The Big Bang becomes a bounce, not a creation, and the first universe disappears. In its place is an endless sequence of cosmic eras, each one inheriting something from the last. Classical oscillatory models were once the simplest version of this intuition. Gravity pulls everything back, the cosmos crunches, then somehow restarts. But classical cycles face hard problems, especially entropy, which in plain language is the tendency for usable order to degrade. Each cycle tends to accumulate disorder, making later cycles larger and longer, and making a past eternal sequence difficult to sustain. Even the radiation left over from previous cycles becomes a burden, because it changes the dynamics of the next contraction. Modern cyclic thinking shifts the mechanism away from a purely classical crunch. It asks whether quantum gravity changes the rules at extreme density, where space-time itself may become granular. In that regime, collapse might not end in a singularity. It might trigger a rebound because the geometry cannot compress indefinitely, the way matter resists being squeezed beyond certain quantum limits. Loop quantum cosmology offers a concrete example in accessible terms. It applies ideas from loop quantum gravity to the universe as a whole, treating space-time geometry as quantized. Instead of a smooth continuum that can shrink without limit, space has discrete units that resist being squeezed beyond a minimum scale. At ordinary densities, general relativity is recovered, so the model agrees with what we already test. The novelty appears only when curvature becomes so extreme that the granularity can no longer be ignored. Near the would-be singularity, the quantized geometry produces an effective repulsive contribution. Gravity still attracts, but the quantum structure pushes back when density approaches a critical value. The result is a bounce that replaces infinite curvature with a finite maximum, and the equations remain well-defined across the transition. Time can extend through the bounce, making our expanding universe the aftermath of a previous contracting phase. Visually, the timeline bends like a spring, compression, recoil, and release. If that happened, the next question is what survives the reset. A bounce is not automatically a clean slate, and physics rarely forgets everything. Entropy is the first complication, because a prior universe would have generated enormous disorder through star formation, nuclear burning, and black hole growth. Some bounce models try to dilute entropy through vast expansion phases, or relocate it into degrees of freedom that do not reheat our observable patch. Others rely on the idea that what we call our universe may be a limited region, not the whole global space-time. Even if most details are erased, subtle traces could carry over, and those traces would be the scientific prize. Leftover anisotropies might bias the early expansion, leaving preferred directions or unusual alignments in the sky. A background of primordial gravitational waves could pass through the bounce more easily than matter, because gravitational waves interact weakly and do not thermalize easily. Tiny imprints might remain in the CMB as non-standard correlations, or in the distribution of large-scale structure as unexpected patterns. The challenge is that these signals would be faint, and faint signals are where false positives love to hide. This is where the documentary's hook becomes a testable tension. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? The CMB is not just a baby picture, it is also a forensic surface where minute temperature variations encode earlier dynamics, acoustic oscillations, gravitational potentials, and the subtle hand of expansion. On screen, those variations can be shown as ripples frozen into light, like sound waves turned into color. The peaks and troughs in the CMB power spectrum are not decorative statistics, because they reflect real physics. They record how pressure and gravity competed in the primordial plasma, setting a characteristic scale. Any pre-Big Bang influence would have to thread its way through that well-measured pattern without breaking what already matches. Another radical proposal reaches the same conclusion by a different route. Penrose's conformal cyclic cosmology argues that the far future of our universe can be mathematically reshaped into a new Big Bang. In the remote future, after stars die and black holes evaporate, the universe could be dominated by radiation and extremely dilute energy. In that limit, the distinction between large and small scales can blur under conformal transformations. The end becomes, in a precise mathematical sense, compatible with a new beginning. CCC hinges on a strange kind of forgetting, and it is easy to misunderstand without a concrete image. Massive particles define clocks and rulers, but if mass effectively disappears from the relevant description, only light-like behavior matters. Without mass scales, the universe can be stretched or shrunk without changing the physics of those massless degrees of freedom. Penrose suggests that the cold, empty end of one eon becomes conformally equivalent to the hot, dense beginning of the next. The universe, in this view, is not recycled by force, but by symmetry. In that picture, our Big Bang is not a bounce from contraction. It is a redescription of an exhausted cosmos whose remaining content behaves like radiation. The previous universe ends not with a crunch, but with a long fade into near featurelessness. The last dying light becomes, after a mathematical rescaling, the first light of a new era. The transition is less like a collision and more like a change of coordinates, an elegant, unsettling relabeling. CCC also makes claims about possible observational signatures. Penrose and collaborators have argued that events in a previous eon, like supermassive black hole encounters, could leave circular features in the CMB. These are described as low-variance circles, regions where temperature fluctuations are unusually uniform. The idea is that violent bursts of energy could propagate through the conformal boundary and seed subtle patterns. If true, the sky would contain scars from a time that is not supposed to be ours.
The controversy is immediate and technical, and it matters for credibility.
The CMB is noisy, and random fields naturally contain circles of many kinds. Statistical significance depends on how you search, how many patterns you allow, and how you correct for selection effects. Foregrounds from our galaxy, instrument systematics, and data processing choices can mimic or erase delicate signals.
Even the act of masking the Milky Way can create artifacts, because removing data changes what patterns look rare.
So the chapter's tension is not only philosophical, it is methodological, because extraordinary claims live or die on careful inference. If we claim the universe has memory, we must show that the memory is not a mirage produced by our own pattern hunting. The same human instinct that finds faces in clouds can also find circles in cosmic noise, unless the statistics are ruthless.
Still, the unsettling narrative remains, because the alternatives are not easily dismissed.
A previous cosmos could have ended in heat death, stretched thin until only cold radiation remained. It could have ended in a crunch, collapsing into a state where quantum geometry forced a rebound. Or it could have ended in something stranger, where the meaning of time and scale dissolved before any final moment.
Each ending is a different answer to what it means for the universe to finish. Each ending changes what before means. In a bounce, time continues through the high-density bridge, so before is earlier in the same temporal sequence. In CCC, before is a prior eon connected by conformal equivalence, where the usual measures of time and size lose their authority. In both cases, the Big Bang stops being a first cause and becomes a transition. The beginning becomes a boundary condition, not a metaphysical starting gun.
We return to the evidence we trust, because mystery without anchors becomes fantasy. The CMB, large-scale structure and primordial elements, confirm an early hot phase, but they do not certify an absolute beginning. The singularity problem tells us our main theory breaks exactly where we most want certainty. Cyclic and conformal models exploit that gap, offering ways the universe could be older than its oldest light.
They do not overthrow the Big Bang's successes, but they reinterpret what the Big Bang signifies. If we are living in the ashes of something else, then our origin story changes from creation to inheritance. The first moments of our universe might be shaped by conditions we did not generate, like a melody that begins mid-phrase. That is the terrifying twist, because it implies our cosmos may carry debts from an earlier one. Our universe could be a sequel, and the prologue might still be written into the sky, encoded in correlations we have not fully learned to read. Now the question tightens into a final, practical edge. If a previous universe existed, what was it made of at the end? Was it matter, radiation, dark energy, or something closer to nothing? And if it was almost nothing, what does it mean for nothing to still have enough structure to become everything we see? Chapter 1 left us at a boundary where classical space-time stops giving answers, and where our familiar intuitions begin to slip. Now the question tightens into a final, practical edge. If the prior state was almost nothing, what does nothing mean in physics? The central question returns with a trap built into its grammar, because the words themselves smuggle in a timeline. Did anything exist before the Big Bang? And if time began there, what could before even mean? In standard cosmology, time is part of the universe's geometry, not an external stage where events line up. When cosmologists say the Big Bang, they do not mean an explosion into pre-existing emptiness like shrapnel into a room. They mean the earliest hot, dense phase our equations can reliably describe, traced back to a limit where densities and curvatures become extreme. At that limit, the coordinate we call time may lose its usual meaning, because the geometry that defines it is itself in question. If the Big Bang is the first moment of time, then asking what happened earlier may be like asking what is north of the North Pole. The metaphor is useful because it highlights a category mistake. not because the universe is literally a globe. North is defined on the surface, and it fails at the pole because the coordinate system runs out. Yet our minds demand causes because causes feel older than effects, and the demand is stubbornly human. We imagine a chain that must extend backward, even if the chain includes time itself. That tension is not a poetic problem. It is a technical one, because theories of origin must define the parameter that counts as time. In general relativity, time is not a universal metronome ticking outside the cosmos. It is woven into space-time, and different observers can slice that space-time into nows in different ways. Near a singularity, those slices can become ill-behaved, and the very notion of a global clock can break. So the question, what happened before, becomes two questions that sound similar but are not. First, did the universe have an earlier phase described by some deeper theory? Second, is there any meaningful earlier at all, once time is no longer fundamental? Physicists use the word nothing in several different ways, and the differences matter more than the drama. The first meaning is empty space, a classical vacuum with no matter present, like a perfectly cleared stage. The second meaning is no particles, but quantum fields still exist everywhere, even when detectors are quiet. The third meaning is no classical space-time at all, where geometry is not yet a smooth continuum. The fourth meaning is philosophical nothing. No laws, no fields, no mathematics, no possibilities. Most scientific creation from nothing proposals use the third meaning, not the fourth. And that distinction is the hinge. They aim for no classical space-time, but they still rely on quantum rules that assign amplitudes and probabilities. They still assume a framework where something like a wave function can be written down, even if it is only formal. The hidden terror is that the word nothing becomes a placeholder for assumptions we do not name. To see why, we have to clarify the quantum vacuum in plain terms, without turning it into mysticism. In quantum field theory, fields are fundamental, and particles are excitations of those fields, like quantized ripples. A vacuum is the lowest energy state of the fields, not the absence of the fields. Even with no particles present, the fields cannot be perfectly still, because perfectly still would require forbidden precision. The uncertainty principle is the simplest doorway into this idea, and it is not about measurement clumsiness. It is a structural feature of quantum theory, encoded in the non-commuting nature of certain variables. It limits how precisely certain pairs of quantities can be fixed at once, such as field amplitude and its conjugate momentum. For fields, that means the vacuum has unavoidable fluctuations around its minimum energy configuration. These fluctuations are not tiny classical waves traveling through space. They are probabilistic variations in field values that appear in calculations and in measurable effects. If you could watch the vacuum with impossible eyes, the visuals would not be a froth of little particles popping like bubbles. It would be a restless statistical texture, correlations waxing and waning, because the vacuum is a quantum state with structure. In that sense, empty space is closer to a tuned instrument than to a blank void. The vacuum has structure because quantum fields have modes, correlations, and a ground state energy that cannot simply be set to zero everywhere. That structure shows up in phenomena like the Casimir effect, where boundaries change the vacuum energy and produce a force. Two uncharged metal plates, placed micrometers apart, feel a tiny attraction because the allowed field modes between them differ from those outside. The Casimir force is small, but it is conceptually loud because it turns nothing into something that can push. It also echoes through other effects, like the Lamb shift in atomic spectra, where vacuum fluctuations subtly alter energy levels. Empty space, in this sense, behaves like a medium with rules, even when it carries no classical matter. This is where the opening hook gains a sharper edge, because it reframes the universe's earliest fingerprints. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? Some of that memory could be the imprint of vacuum fluctuations stretched to cosmic scales, preserved like faint grain in a photograph. When we look at the cosmic microwave background, we do not see a perfectly smooth glow. We see a nearly uniform temperature with tiny variations, 1 part in 100,000, mapped across the sky. Those variations are not noise. They are the seeds of later structure, and in many models they originate as quantum fluctuations. The early universe may have amplified microscopic uncertainty into macroscopic structure, turning quantum randomness into galaxies. The idea is counterintuitive, but the mechanism is concrete. Expansion can take a fluctuation that begins smaller than an atom's nucleus and stretch it until it spans light years, then millions of light years. Inflation enters here as context because it is our best developed amplifier, and it is built to answer specific puzzles. Inflation proposes a brief era of extremely rapid expansion in the early universe, driven by a high-energy state with negative pressure. In simple terms, space itself expands so quickly that regions once close become causally separated. It explains why distant regions look similar in temperature, solving the horizon problem, because they were once in contact before inflation blew them apart. It also drives the universe towards spatial flatness, addressing the flatness problem, because rapid expansion dilutes curvature, the way a balloon's surface looks flatter as it grows. For visuals, imagine a tiny patch of patterned fabric being pulled taut until the pattern becomes almost uniform. The stretching does not erase the pattern entirely. It smooths it while preserving faint variations, which later become the scaffolding for structure. Inflation also offers a mechanism for the seeds of galaxies, and it does so with calculable statistics. Quantum fluctuations in the inflaton field are stretched by expansion and become density perturbations, which later grow under gravity into the cosmic web we map today. This is not a vague story, because the predicted spectrum is close to what the CMB measures. The spectrum is nearly scale invariant, meaning fluctuations have almost the same strength across a wide range of sizes, with a slight tilt. That tilt, measured by missions like WMAP and Planck, is one of inflation's strongest empirical successes. The CMB also shows the fluctuations are close to Gaussian, a signature consistent with simple quantum origins. But inflation does not automatically answer the origin question, and this is where the story tightens again. Most inflation models require a pre-existing field, a potential energy landscape, and an initial patch where inflation can begin. They require a state that is already something, even if it is simple. Inflation explains how a small region becomes our observable universe, not why there is a region at all. It tells us how the universe evolves once inflation starts, but it does not, by itself, tell us why the inflaton existed, or why its initial conditions were suitable. The beginning of inflation becomes a new boundary, and the old question reappears there. So the Big Bang, in this view, is not a proven birth event. It is the point where we switch descriptions, from unknown initial conditions to a hot, expanding phase. If we want from nothing, we need a proposal that does not assume classical time before the beginning, and that is a high bar. One famous attempt is Alexander Vilenkin's tunneling proposal, which treats the universe as a quantum system rather than a classical object. It suggests the universe could nucleate by quantum tunneling from nothing. Here, nothing means no classical space-time, not an empty room waiting to be filled. The proposal treats the universe itself as having a wave function. Tunneling is a quantum process where a system crosses a barrier it cannot cross classically, and it is not merely a metaphor. A simple analogy is a ball that appears on the other side of a hill without climbing over it, because the wave function spreads. In quantum mechanics, the wave function can have amplitude on both sides of a barrier. The barrier suppresses the probability, but it does not make it exactly zero, and that not zero is the crack in the classical wall. In atomic physics, tunneling explains phenomena like alpha decay, where particles escape a nucleus despite insufficient classical energy. In cosmology, the object that tunnels is not a particle in space. It is the universe's configuration. In Vilenkin's picture, the barrier is not a wall in space. It is a barrier in the space of possible geometries and sizes of the universe, a landscape of configurations. The universe begins as a tiny, closed geometry, then tunnels into a state where it can expand. After nucleation, inflation can take over and blow that tiny beginning into a vast cosmos. For visuals, the space of possibilities is hard to show, so we translate it into something the eye can hold. A dim, abstract landscape appears, curves representing allowed geometries. Then a small, bright bubble forms, as if a new region of reality has clicked into place. The bubble is not inside space. It is the first hint of space. This proposal is terrifying in a specific way, because it shifts the meaning of cause. It suggests that existence can be a quantum event, not a classical trigger pulled by something outside. It replaces a creator-like push with a probability amplitude.
It makes the beginning less like an explosion and more like a spontaneous transition. But the proposal still carries hidden structure, and the structure matters because it is doing the explanatory work. It assumes quantum mechanics applies to the whole universe, even when there is no external observer. It assumes a notion of a wave function and a rule for calculating probabilities. It assumes a mathematical space where nothing and something are neighboring configurations.
That last assumption is subtle, because it means we are already inside a framework where possibilities exist. The nothing is not the absence of all description. It is a boundary condition in a theory, defined by the theory's own language, and that language is not nothing. A second major attempt is the Hartle-Hawking no-boundary proposal, which aims to remove the sharp edge altogether. It does not picture a universe tunneling from nothing into time.
It pictures the beginning as a region where time behaves like a spatial dimension.
The universe is finite but unbounded, like the surface of Earth. The Earth analogy is about edges, not about size, and it is worth lingering on the geometry. On a sphere, you can travel without hitting a boundary, even though the surface area is finite. There is no special cliff where the surface ends. Hartle and Hawking suggest the early universe is like that in time, where the past direction smoothly closes.
To ground this, we need one technical distinction stated carefully, because it is easy to misunderstand.
Lorentzian time is the time of everyday physics, with one time dimension and a signature that distinguishes time from space. Euclidean time is obtained by a mathematical rotation that makes time behave like another spatial coordinate, smoothing certain infinities.
In many quantum gravity calculations, Euclidean geometries make path integrals better behaved, because oscillatory phases become decaying exponentials. This is a mathematical move, but it has physical implications for which histories contribute most. The no-boundary idea uses a Euclidean region near what we call the beginning, where the geometry is regular and closed. In that region, the geometry has no boundary in the past direction, because the time coordinate becomes like latitude on a sphere. Then, as the universe grows, the description transitions into Lorentzian time, where time behaves normally and expansion proceeds. The transition is not a switch you could watch on a clock. It is a change in the most useful description. Path integrals are the language often used to express this, and they carry a particular kind of intuition.
In quantum theory, you can compute amplitudes by summing over many possible histories, each weighted by a phase. In quantum cosmology, the histories are different space-time geometries and field configurations. The no-boundary proposal specifies which histories are included by requiring regular, boundaryless geometries. The key claim is not that time literally turns into space, as if a dimension changes its identity.
The claim is that the quantum description near the origin is best captured by Euclidean geometry, which avoids a singular boundary. That choice changes what initial condition means. Instead of specifying a starting state at a first time, you specify a smooth closure condition. This also changes the emotional shape of the question, and that shift is part of why the idea is so compelling. If there is no first moment, then the demand for a cause at t=0 loses its target. The universe does not begin at a sharp edge. It emerges from a rounded geometry where the concept of earlier time is not defined. Both Vilenkin and Hartle-Hawking aim to avoid a classical singularity, and both treat the early universe as a quantum object.
Both still rely on a mathematical framework that is very far from philosophical nothing. The difference is in the boundary condition and in how they interpret the emergence of time, whether by tunneling or by smooth closure. To keep the mystery honest, we have to talk about energy bookkeeping, because nothing often gets sold as an accounting trick. A common popular claim is that the universe could come from nothing because the total energy is zero. The idea is that positive mass energy can be balanced by negative gravitational potential energy. In some cosmological models, this balance can make the net energy of a closed universe vanish. This is speculative and subtle, because energy in general relativity is not defined globally in the same way as in Newtonian physics. In curved spacetime, the conservation laws we love become local statements, tied to symmetries through Noether's theorem. In an expanding universe, defining total energy depends on symmetries and boundary conditions, and those may not exist in the needed form. Still, the intuition matters for why almost nothing is not obviously forbidden by a simple conservation argument. If the net energy can be zero, then creating a universe may not require borrowing energy from an external account. It reframes the question from where did the energy come from to why is there a lawful structure that permits such a balance? Even if the net is zero, the universe is not nothing, and the distinction is more than philosophical hair-splitting. A zero balance can still include fields, geometry, and the rules that relate them. It can still include a probability distribution over possible beginnings. The terror is that our deepest explanations often end by assuming the very structure we hope to derive. This is the philosophical trap of smuggling in hidden assumptions, and physics is not immune to it. When physicists say nothing, they often mean no classical space-time and no particles. They do not mean no quantum fields, no Hilbert space, no action principle, and no measure. The framework remains, and it quietly does the creative work. That does not make the proposals meaningless, and it does not reduce them to wordplay. It clarifies what kind of answer they are and what kind they are not. They are attempts to replace a singular beginning with a quantum boundary condition, so the origin becomes a calculable question rather than a breakdown. They aim to show that a universe like ours is not an impossible special case, and that the laws we know might naturally allow such a history. But then a harder question waits behind the curtain. Why these laws? And why a quantum arena in which histories can even be discussed? The next question is what these ideas predict, because cosmology is constrained by data, not by elegance alone. Inflation already gives us a handle through the spectrum of primordial perturbations. Quantum creation proposals may influence which inflationary initial conditions are likely. They may also affect the probability measure over different histories, which changes what outcomes are expected. Measures are a technical headache with big consequences, and the headache is not optional. If many universes or many histories are possible, you need a rule for weighting them. Otherwise, probability statements float. Different measures can make the same theory predict very different typical universes. Without a principled measure, likely becomes a word without a stable meaning. This is where the narration's calm tone hides a sharp point, because it touches the limits of scientific inference. A theory can generate an enormous space of possibilities, but observation samples only one history, ours. How do you compare a single data point to a distribution over universes, especially when the distribution depends on choices in the formalism? Some proposals suggest signatures in spatial curvature, and curvature is one of the few global features we can attempt to measure. A universe created as a small, closed geometry might leave a preference for slight positive curvature, even after inflation dilutes it. Observations currently constrain curvature to be very close to flat, but not exactly proven flat. Future surveys could tighten this and either squeeze or support certain nucleation pictures. Other potential constraints involve primordial gravitational waves and the detailed statistics of CMB fluctuations. Gravitational waves from inflation would imprint a distinctive polarization pattern in the CMB, and their amplitude relates to the energy scale of inflation. The no-boundary proposal, in some treatments, affects the weighting of perturbation modes, especially on the largest scales. That could influence the expected amplitude of large-scale fluctuations. These are delicate effects, and they compete with uncertainties in inflation models themselves, which come in many variants. Some models predict more gravitational waves, some predict fewer, and some alter the shape of non-Gaussian features. The observational game becomes a triangulation, where multiple measurements constrain a web of possibilities. The universe, in this sense, is not only a story, it is a statistical object. There is also the question of whether these proposals can be made consistent with a full theory of quantum gravity, rather than a controlled approximation. Quantum cosmology often uses simplified models called mini-superspace, where only a few degrees of freedom are quantized, such as the scale factor and a homogeneous field. That makes the math tractable, but it risks missing essential physics, like inhomogeneities or topology changes. A complete theory would need to explain why the simplification is justified and what corrections it demands. It would need to tell us whether wave function of the universe is a deep concept or a convenient handle. It would also need to clarify what counts as an observation when there is no outside observer, a problem that sits at the intersection of cosmology and quantum foundations. Historically, these ideas grew out of the same discomfort that drove singularity theorems, and the timeline matters. In the 1960s and 70s, the Hawking-Penrose singularity theorems showed that, under broad conditions, classical general relativity predicts singularities. Those theorems did not prove the Big Bang was a physical point. They proved the classical description becomes incomplete. Then Hawking's work on black hole radiation showed that quantum effects matter when gravity is extreme, and that horizons have thermodynamic properties. That result made the union of quantum theory and gravity feel unavoidable, not optional. It encouraged the idea that the universe's beginning should also be treated quantum mechanically, because the early universe is the ultimate strong gravity regime. The no-boundary proposal was part of that broader attempt to make the beginning a calculable object, rather than a place where equations stop. Vilenkin's tunneling picture, emerging in the same era of quantum cosmology, offered a different boundary condition with a different intuition. These were not isolated speculations. They were responses to a shared problem. The classical singularity is a signpost that new physics is required. Still, the most honest outcome may be that from nothing is a limit concept, and limits reveal what a theory cannot say. It is a way of pushing explanations to the edge of what our formalism can express. The closer we get to nothing, the more we rely on mathematics to say what nothing could even be. The universe becomes a question about why there are rules at all. At this point, the visuals should slow down, because the ideas become abstract while the stakes become intimate. A dark screen, a faint grid that dissolves, then a gentle emergence of geometry, lines curving into a closed surface, suggests the no-boundary rounding. Then the image shifts to a probabilistic haze, where a tiny, bright region appears, suggesting tunneling without depicting a literal location. This chapter's terror is not that the universe came from a void, as if emptiness suddenly panicked into existence. It is that the void, in physics, is never truly empty, and our cleanest definitions still carry structure. Even the cleanest vacuum is a state with properties, and even the cleanest origin proposal assumes a framework. We may be trying to explain existence using tools that already presuppose existence. And yet, the proposals do something important, and the importance is scientific as much as philosophical. They show how the Big Bang might be a frontier, not a first moment, because the beginning can be replaced by a boundary condition. They show how time could emerge from a regime where time is not fundamental, at least in the classical sense. They show how causality might be an approximate concept that only applies after the universe becomes classical. That last point is easy to say and hard to absorb, because causality feels like the skeleton of reality. If causal order depends on a classical space-time structure, then at the deepest level, the universe may not be arranged as a simple chain. Instead, it may be arranged as a quantum superposition of possibilities, from which a classical history condenses. So we end with a transition that opens the next door, and the door is not subtle.
If one universe can appear from a vacuum-like state, why not many, endlessly? If the mechanism is quantum and probabilistic, then rarity becomes a parameter, not a prohibition. The idea of nothing begins to look less like a blank and more like a factory. The central question remains, but it changes its shape as we stare at it longer. Did anything exist before the Big Bang? And if time began there, what could before even mean?
If time is emergent, then before may be a category error. And the deeper question becomes why there is a lawful quantum arena at all. That is where the mystery stops being about our universe and becomes about reality's capacity to produce universes endlessly. Chapter 2 ended with a door left open. If one universe can nucleate from a vacuum-like state, why not many, endlessly? The central question returns with new pressure because it refuses to stay philosophical. Did anything exist before the Big Bang? And if time began there, what could before even mean? On screen, the familiar cosmic timeline appears, brightening from darkness into a hot, granular fog.
The line looks clean, yet the moment labeled t=0 is more like a warning sign than a destination. Our universe looks strangely calibrated for complexity, and the calibration shows up in equations as much as in starlight. The cosmological constant is small enough to permit galaxies, not instant dilution. In Einstein's field equations, that constant behaves like a uniform energy density of empty space.
In plain language, it is a pressure that can push the universe apart, even when matter thins out. If it were much larger and positive, space would accelerate too quickly for gravity to gather gas. If it were large and negative, the universe could recollapse before long-lived stars ever ignite. Particle masses and force strengths also sit in narrow ranges, and those ranges are not aesthetic. Shift them slightly and chemistry collapses, or stars never stabilize. The electron's mass sets the size of atoms, while the proton's mass anchors nuclei against thermal agitation. The electromagnetic coupling fixes how tightly electrons bind, and it decides which elements can form stable molecules. Even the strong nuclear force appears delicately placed between two failures. Weaken it, and deuterium becomes unstable, choking off stellar fusion. Strengthen it, and almost all hydrogen converts early, leaving little water-friendly chemistry. This is the fine-tuning problem in its least mystical form. The constants look selected, yet physics offers no obvious selector. Historically, the discomfort sharpened in the late 20th century as cosmology became precision science. When satellites mapped the cosmic microwave background, the numbers stopped being vague, and the coincidences became harder to ignore. One response is to widen the stage, not by adding new forces, but by multiplying arenas. If many universes exist with varied constants, then we observe a compatible one. That move is not comfort, because it changes the kind of explanation we are allowed to want. It replaces a single miracle with an enormous machine that produces every option. Visually, imagine a dark ocean of space that never stops swelling, with bright pockets flashing into existence like embers. Each ember is a universe with its own rules, and most of them never host a single observer. Inflation is the hinge because it already reshaped early universe thinking, and it did so for practical reasons. It explains smoothness, flatness, and quantum seeds stretched cosmic. The smoothness problem asks why distant regions share nearly the same temperature despite limited time to communicate. Inflation answers by making those regions once close enough to equilibrate before expansion carried them far apart. The flatness problem asks why space is so close to geometrically flat today. Exponential expansion drives curvature toward zero, much like zooming in on a sphere makes the surface look locally flat. Inflation also gives a mechanism for structure, and it is almost unsettlingly minimal. Quantum fluctuations, tiny, unavoidable jitters in fields, are stretched into macroscopic density variations that later become galaxies. But inflation can do more than start our hot phase. In many models, inflation never ends everywhere at once. Eternal inflation proposes a global space-time still inflating, even while local regions stop. Local regions stop inflating and become bubble universes like ours. Inside a bubble, inflation ends and energy converts into particles, and that conversion is not optional. That conversion is reheating, and it looks like a Big Bang. So the Big Bang becomes a local event, a beginning with an address. It is the start of our hot, dense phase, not necessarily the start of existence. The engine is a scalar field, often called the inflaton, and it is defined by its value at each point in space. Unlike a vector field, it has no direction, only magnitude, so it can fill the universe uniformly. Its potential energy acts like a vacuum energy, producing negative pressure in the stress-energy tensor. In plain terms, it makes gravity effectively repulsive on large scales, so space accelerates outward. In simple terms, the field sits high on a potential landscape like a ball balanced on a plateau. While it lingers, space expands exponentially. The word exponentially matters because it is not just fast, it is compounding. In a tiny fraction of a second, distances can double again and again, erasing earlier irregularities as if they were never there. Eventually, the field rolls down or transitions to a lower state, and the details depend on the shape of the potential. In some regions it does so, in others it does not. Quantum fluctuations make this uneven, and they are not merely noise added afterward. During inflation, fluctuations in the inflaton field become fluctuations in when inflation ends, which becomes fluctuations in density. Some patches decay early, some late, and some get kicked back upward, as if random jolts keep them hovering. That stochastic behavior is why inflation can be eternal. Expansion outruns decay, so inflating volume keeps growing overall, even if many regions exit. The factory does not need to be stable everywhere. It only needs some regions to keep inflating faster than others stop. The multiverse picture is then geometric, and it invites a particular kind of visualization. A parent inflating background spawns bubbles, each with its own internal history. From far away, the background looks like a smooth, accelerating fabric, but it is riddled with sudden transitions. Each transition is a bubble nucleation event, an abrupt change of state that creates a new domain. To make this concrete, cosmologists use the language of false vacuum decay, borrowed from quantum field theory. A false vacuum is a metastable energy state. Metastable means it can persist for a long time, even if it is not the lowest energy configuration. It is not the lowest energy state, but it is locally trapped. A familiar analogy is supercooled water, which can remain liquid below freezing until disturbed. It can remain liquid below freezing until a disturbance triggers crystallization. In field theory, the disturbance can be quantum tunneling, which is not a classical climb over a hill. The field transitions through a barrier in its potential, appearing on the other side without traversing intermediate states. When tunneling occurs, a bubble of true vacuum nucleates, and the word bubble is more than metaphor. The new phase occupies a finite region, bounded by a wall where the field changes rapidly. That wall has energy, and in relativistic terms it carries tension, like a stretched membrane. The bubble expands at near light speed through the false vacuum. Inside, the vacuum energy is lower, and dynamics change, including how quickly space expands. Outside, the false vacuum keeps inflating, and it can stretch away the collision front as it tries to catch up. That change is a phase transition in the early universe sense, and it echoes older transitions in particle physics. It is not a material substance changing, but a field state changing. In the early universe, we already expect phase transitions, like electroweak symmetry breaking and quark confinement. Those transitions reorganize what particles even mean, because particles are excitations of fields whose properties depend on the vacuum. The energy difference does not vanish because energy conservation still rules the accounting. It becomes kinetic energy of fields and then a hot plasma of particles. That is reheating in one sentence, but the process has texture. Vacuum-like energy becomes radiation and matter, and temperature becomes meaningful again. As reheating proceeds, particle species are produced, scatter and thermalize, and the universe becomes an opaque soup. Photons, electrons, quarks and gluons collide constantly, and the concept of a free path is almost non-existent. Our Big Bang in this framing is reheating inside one bubble, and the timing matters. It is a thermal beginning, not an absolute beginning. The familiar Big Bang narrative, hot, dense, expanding, still holds within the bubble after reheating. What changes is the claim that the hot phase marks the start of all reality. This reframes the opening hook without softening it, because it makes the mystery more mechanical. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? The memory is not a literal recollection, but a set of boundary conditions that look chosen. Why these constants? Why these initial smoothness conditions? And why a universe that can grow complexity rather than dissolve into featureless expansion? Eternal inflation makes before ambiguous, because it separates local time from global description. There can be a parent space-time where time continues, even if our bubble's time begins at reheating. Inside our bubble, you can trace proper time back to a hot, dense state, and the equations remain well behaved. Outside, the inflating background has its own clock, defined by the evolution of the inflaton field and the expansion of the metric. Yet the ambiguity cuts both ways, because inflation does not automatically erase every beginning. Even in eternal inflation, singularities may still lurk in the parent spacetime. The Born-Guth-Vilenkin result is often cited here, and it carries weight because it is not tied to one specific inflaton potential. Many inflating spacetimes are past incomplete under broad conditions. Past incomplete does not prove a first moment, and it does not declare a singularity in the usual sense. It says the inflating description cannot be extended indefinitely into the past. In other words, if the average expansion rate along a past-directed world line is positive, that world line cannot be extended forever backward. Something else must take over, another phase, another boundary condition, or a deeper theory. So the factory may be endless forward, yet still require some boundary behind it. The terror shifts, but it does not disappear. On screen, the inflating background recedes into darkness, and the camera tries to follow it backward. The further it pulls, the more the picture breaks into abstraction, as if the film itself cannot render what comes earlier. If bubbles are real, we can ask for evidence, and the question becomes almost forensic. The cleanest hope is collisions between bubbles in the early epoch. A collision would disturb our bubble's early conditions, and it would do so in a specific geometric way. It could leave anisotropies or localized features in the CMB. The cosmic microwave background is a relic radiation field from when the universe first became transparent, about 380,000 years after reheating. It is a snapshot of tiny temperature differences which correspond to density differences that later grow into structure. A bubble collision, if it happened before that snapshot, could imprint a disk-like feature, because the intersection of two expanding bubbles projects as a circle on our sky. The circle would not be a perfect ring, but a region with a subtle statistical oddness. Possible signatures include circular temperature anomalies or unusual polarization patterns, especially in the E-mode polarization field. They would be subtle and easy to overinterpret. Detection is difficult for basic reasons, and the first is simply that we have one universe to examine. We see only one sky, and cosmic variance limits certainty at the largest scales. Cosmic variance is the unavoidable uncertainty from having only one realization of the random process that seeded fluctuations. Even with perfect instruments, the largest angular scales offer few independent modes, so anomalies can appear by chance. Foregrounds from the Milky Way complicate the map, because our galaxy glows in microwaves through dust and synchrotron emission. Instrument systematics and data processing can create look-alike patterns. Even if a feature is found, interpretation is controversial, because inflation itself can produce rare-looking features. Many inflationary models can mimic localized anomalies without collisions. So the multiverse remains inference-heavy, and that is a scientific discomfort, not a poetic one. It is motivated by theory and fine-tuning, not by a single decisive observation. Still, it is not empty speculation, because it is anchored to mechanisms we already use. If inflation is real, and if quantum fields can tunnel, then bubble nucleation is not an exotic add-on. It is a natural extrapolation. Then a deeper problem appears, and it is technical but central. In an infinite multiverse, how do you define probabilities? In everyday life, probability is counting outcomes in a finite sample space, or measuring frequencies in repeated trials. In an eternally inflating multiverse, the trial never ends, and the sample space is not just large, it is infinite. If inflation is eternal, it produces infinitely many bubbles, and within them, infinitely many galaxies. Counting outcomes becomes ill-defined, because every outcome occurs infinitely often. This is the measure problem, and it is not a minor bookkeeping issue. Probabilities depend on how you regulate infinities, and different regulators give different answers. One attempt uses a time cutoff, and it sounds straightforward until you try to define time globally. You count bubbles before a chosen time, then take a limit as the cutoff goes to infinity. But the result can depend on the time variable you chose, because general relativity allows many slicings of space-time. Different slicings of space-time can reorder events and change ratios. A cutoff based on proper time can favor rapidly expanding regions, producing paradoxical predictions like the youngness problem, where most observers should find themselves in extremely young universes. A different time parameter can soften that, but then the choice looks arbitrary. Another attempt uses a scale factor cutoff, which tracks expansion rather than clock time. It counts events before expansion reaches a threshold, trying to reduce gauge dependence. Other measures focus on causal patches, restricting attention to what can influence a single world line. They restrict attention to what can influence a single world line, avoiding global infinities. A causal patch approach feels conservative because it never asks you to compare disconnected infinities. Yet it raises its own questions about what counts as a representative world line and whether the restriction hides important global structure. None of these choices is obviously unique, and that is the wound that will not close. The multiverse can become a theory that predicts almost anything, depending on the measure. That slipperiness matters because fine-tuning arguments rely on probability, even when they try to sound modest. If you cannot define typicality, selection arguments weaken. When someone says, most universes would not allow observers, the word most is doing heavy lifting. In an infinite set, most depends on the rule you use to compare infinities, and different rules can reverse conclusions. Still, the measure problem is not a fatal flaw by itself, and it may be a clue. It may be a sign we are missing a deeper principle. Historically, physics has faced similar moments where infinities signaled incomplete understanding. The ultraviolet catastrophe pointed toward quantum theory, and the infinities of early quantum electrodynamics demanded renormalization and new conceptual discipline. The multiverse measure problem may be another such warning, suggesting that our current language is not the final one. Perhaps the correct theory will define probabilities intrinsically, without arbitrary cutoffs. The multiverse also connects to high-energy theory in a specific way, and the connection is not merely aesthetic. String theory suggests an enormous landscape of vacuum states. A vacuum state here means a stable or metastable configuration of fields and geometry, not an empty container. It determines low-energy physics, including particle spectra and constants. In string theory, extra dimensions must be compactified, curled into shapes too small to see directly. The shape, size, and topology of that compact space influence which particles appear and how they interact. Fluxes, field lines threading cycles in the compact dimensions, can take many discrete values like quantized choices. Different compactifications and flux choices yield different effective laws. The number of possibilities is often described as vast, sometimes quoted in numbers that strain intuition. The exact count is model-dependent, but the conceptual point is that there may be many consistent vacua, not just one. In that context, eternal inflation becomes a population mechanism, a way to realize many vacua as actual regions. It can sample the landscape by creating bubbles in different vacua. A bubble that lands in one vacuum might have a different cosmological constant, different symmetry breaking, and different particle masses. Another bubble might never form stable atoms, or might expand too fast for any structure to persist. Then anthropic reasoning enters, reluctantly, because it seems to fit the logic of selection. Observers can only arise in regions where structure and chemistry are possible. Anthropic reasoning is not a claim that humans are special, and it is not a substitute for dynamics. It is a selection effect, like noticing you live where air exists. If you find yourself on a planet with liquid water, you should not be surprised that its temperature range allows liquid water. The surprise would be if the laws forced that outcome uniquely, rather than allowing many outcomes and selecting the habitable subset. This is where tension rises, because the method feels like a change in scientific taste. Some physicists see anthropics as the only workable filter, others see it as surrender. The unsettling point is that the multiverse can make fine-tuning feel inevitable, and that inevitability can dull curiosity. It can also make fundamental explanation feel optional. Yet even here the story is not simple, because anthropic arguments can be sharpened into testable expectations. If a distribution over constants can be defined, then one can ask whether our observed values are typical among observer-friendly regions. The cosmological constant is often the flagship example, because its observed value is small but not zero. Some argue that it sits near the upper edge of values that still allow galaxy formation, which would be a suggestive, not decisive, anthropic hint. But without a stable measure, even that hint is fragile, because the predicted distribution depends on how you count universes. The anthropic story is only as strong as the census behind it. So the multiverse is both explanatory and evasive, and that duality is part of its eerie appeal. It can explain why we can exist, while weakening what prediction means. But there is another multiverse idea that does not rely on distant bubbles, and it comes from quantum mechanics itself. The many worlds interpretation treats the wave function as real. It denies a physical collapse during measurement, and instead treats measurement as an interaction like any other. The cost is ontological. You accept that the full quantum state contains all outcomes. Instead, interactions entangle systems with environments, and that entanglement spreads rapidly. The combined state branches into effectively non-interfering histories. Decoherence is the key technical idea, and it is easy to misunderstand. It does not destroy superpositions. It makes interference between branches practically impossible by dispersing phase information into the environment. Each branch contains a definite outcome for observers inside it, because observers are part of the entangled system. All outcomes exist in the full quantum state. This is a multiverse in Hilbert space, not elsewhere in space, and that distinction matters. The worlds are not far away, they are decohered. On screen, the visualization shifts from cosmic bubbles to an abstract tree of branching lines, splitting whenever a quantum event amplifies. The branches do not drift apart in distance, they drift apart in possibility. Many worlds can coexist with inflationary multiverses, but it is conceptually distinct. One multiplies regions, the other multiplies histories. In many worlds, before the Big Bang is not directly answered, and it is not meant to be. It changes what reality means at all times, including the early universe. Yet it adds another layer to the factory metaphor, because it multiplies outcomes even inside one bubble. Even within one bubble, quantum events generate a branching tree of outcomes. Now the question tightens into a different edge, because identity becomes part of cosmology. If reality branches constantly, what counts as a single history? When we say, the universe did this, we may be speaking about a bundle of near-identical branches that diverge in microscopic details. At early times, those details can later amplify, because chaotic systems turn tiny differences into macroscopic changes. Cosmology then becomes a study of typical observers across branches and bubbles, and the word typical starts doing dangerous work. Typical relative to which measure, which branch weight, and which definition of an observer. The disturbing consequence is not only multiplicity, although multiplicity is already dizzying. It is the erosion of the idea of a unique beginning. If bubbles are constantly produced, then no beginning becomes plausible, at least as a practical picture. The Big Bang becomes a local origin story, not the origin. But the parent spacetime may still have boundaries, and that boundary could be conceptual as much as geometric. Even an infinite factory can sit on a finite foundation. This is where the documentary's mystery deepens, because the story refuses to resolve into a single answer. The universe may be older than its oldest light, yet still not past eternal. We are left with a layered picture, and each layer solves one problem while raising another. A hot Big Bang inside a bubble, inside an inflating background, inside a deeper unknown. Fine-tuning becomes less a clue to design and more a clue to sampling. And that is a shift in explanatory style. Our constants may be environmental, not fundamental. Yet environmental explanations demand a census, because environmental implies a population of environments. Without a stable measure, the census becomes an argument about infinities. So the multiverse is both explanatory and evasive, and the tension is not a flaw we can edit out. It can explain why we can exist, while weakening what prediction means. We return to the central question, now reframed by machinery and by mathematics. Did anything exist before the Big Bang? And if time began there, what could before even mean? Inside our bubble, time may begin at reheating, where temperature and entropy become well defined. Outside, time may continue, or it may be replaced by a deeper ordering. Either way, the Big Bang looks less like a first moment and more like a transition, a boundary between phases. It looks like a phase change in a larger system. That larger system may be indifferent to starts and endings because it is governed by statistical processes. It may produce universes the way radioactive atoms produce decays. Radioactive decay is unpredictable for any single atom, yet precisely describable for large populations. In the same way, bubble nucleation could be random in detail, yet governed by rates calculable from field theory. And if that is true, then uniqueness is the illusion, and our sense of specialness is an artifact of perspective. Our cosmos is one outcome among countless others, most forever unobserved. The camera returns to the inflating background, now crowded with bubbles at different stages, some newborn and blazing, some old and cold. The scene is silent, but it feels busy, as if creation has become an industrial process. Now we pivot to the next fear, because the factory has moving parts. If universes are bubbles, what happens when bubbles meet? The transition is unavoidable because expansion does not guarantee isolation forever. Could our Big Bang be the scar of a collision, rather than the quiet birth of a lone bubble? We carry that question forward because it is where theory might touch evidence. The next chapter follows the boundary where bubbles touch and where beginnings may be impacts. Chapter 3 ended with a fear that has moving parts because it imagines universes as bubbles with edges that can drift and meet. If universes are bubbles, what happens when bubbles meet? Do they merge, rebound, or tear each other open? The image is simple, yet it carries a technical sting, because collisions imply a surrounding arena where motion is even possible. This chapter pivots the meaning of the Big Bang. Not creation from nothing, but an impact that made our region hot. On screen, the familiar fireball becomes less like a first spark and more like a flashbulb, an abrupt heating of a pre-existing stage. The question is not only what happened, but what kind of thing can be heated without being created? The central question returns with sharper grammar, because language breaks when it reaches the edge of time. Did anything exist before the Big Bang? And if time began there, what could before even mean?
We use before as if it were a place on a line. Yet physics treats time as part of the geometry that can bend, stretch, and even end. In standard cosmology, Big Bang means an early hot, dense, expanding phase described by the Friedmann equations and a thermal history we can test. It does not automatically mean the first moment of existence, even if popular imagery often suggests that.
When cosmologists say the Big Bang, they usually mean the era when the universe was a plasma, opaque to light, and governed by well-understood particle interactions. The evidence for that hot phase is concrete and oddly intimate, because it sits in the sky like a fossil. The cosmic microwave background, released when electrons and nuclei first formed neutral atoms, is a cooled remnant of that early heat. Its temperature today is about 2.7 Kelvin, and its tiny variations, tens of microkelvin, encode a map of primordial structure. Brain cosmology takes the caution about beginnings and makes it literal, by changing what universe refers to in the first place. Our universe becomes a surface, embedded in a larger, higher dimensional space, with its own geometry and its own notion of distance. Visually, the camera pulls back from a glowing sphere to reveal a thin, luminous sheet, floating in a darker volume that feels more like architecture than emptiness. To say extra dimensions is not to add fantasy space, even though the phrase can sound like science fiction. It is to follow where certain unification attempts naturally lead, when they try to combine quantum mechanics with gravity without mathematical contradictions. The claim is not that dimensions are added for drama, but that the equations demand room to breathe. Historically, the temptation to add dimensions is older than string theory, and it began as a conservative move. In the 1920s, Kaluza and Klein noticed that a fifth dimension could unify gravity and electromagnetism in a single geometric framework. Their idea also introduced a key motif that returns here. Extra dimensions can be hidden if they are compact, curled into tiny circles that ordinary motion cannot resolve. String theory needs additional spatial dimensions for mathematical consistency, because quantized strings behave badly in too few dimensions. In many versions, the critical number is 10 space-time dimensions, where anomalies cancel and the theory remains self-consistent. M-theory reframes them as an 11-dimensional structure with extended objects, suggesting that what looked like separate theories are different limits of one deeper framework. In these frameworks, the fundamental ingredients are not only point particles, which are idealizations that work well until gravity becomes quantum. They include strings and brains, higher dimensional dynamical surfaces that can vibrate, stretch, and carry energy. The vocabulary can feel abstract, yet it is meant to be as physical as a membrane under tension. A brain can have 3 large spatial dimensions, like our everyday world, while still existing inside a higher dimensional bulk. Standard model fields may be confined to it, while gravity can leak into the bulk, spreading along the extra directions. That split is not decorative. It is a mechanism that can make extra dimensions real without making them obvious. That confinement is a crucial move because it explains why we do not see extra dimensions directly in particle experiments or daily life. We are stuck to the brain, like ink on a sheet, able to slide left and right but unable to lift off. The metaphor is imperfect, yet it captures the asymmetry between forces, because electromagnetism and the nuclear forces could be trapped while gravity roams. The bulk is the higher dimensional arena around the brain, and it can carry geometry and fields that our particles cannot access. In a visual sequence, the brain looks like a bright, rippling film, while faint gravitational waves propagate outward into the surrounding volume. The bulk is not outside in the ordinary sense, because it is not a location you could reach by traveling far enough along the brain. Now, the Big Bang can be reinterpreted as a boundary event on the brain, rather than the birth of space-time itself. It is the moment the brain became hot and filled with radiation, initiating the thermal history that leads to nuclei, atoms, stars, and eventually, observers. In this framing, the Big Bang is less like a starting gun for reality and more like the ignition of a particular region's matter content. Ekpyrotic scenarios propose a prehistory that is not expanding, which immediately changes the emotional rhythm of the story. The brain undergoes a slow contraction that prepares the conditions for a hot phase, smoothing the universe before the heating event. The contraction is not a collapse into chaos, at least in the idealized model, but a controlled approach toward a transition. The word ekpyrotic comes from an ancient idea of cosmic fire, associated with Stoic philosophy and the notion of periodic conflagrations. Here it means a smoothing contraction driven by a steep negative potential, a particular shape of energy landscape in field theory. In plain terms, the universe is pulled into a state that erases wrinkles, because the dominant energy behaves like an ultra-stiff substance. In the simplest picture, there are two brains separated along an extra dimension, like parallel sheets with a small gap between them. They move, approach, and eventually collide, with the separation acting like a dynamical variable that can change over time. The approach can be slow and almost silent, which makes the collision feel less like a blast and more like a decisive contact. The collision is not an explosion into empty space, because there is no outside void waiting to be filled by debris. It is an energy transfer, converting brain motion into particles and heat on our brain, as kinetic energy becomes radiation. The visual is a sudden wash of light across the sheet, as if frictionless motion has been converted into a thermal storm. So the Big Bang becomes a bruise, not a birth, and that metaphor is more than poetic.
The observable universe begins as aftermath, not as the start of the stage, because the stage, the bulk and the brains, was already there in the model. A bruise implies an earlier motion and an earlier contact, which is exactly what the scenario tries to formalize. Some versions are cyclic rather than one time, which turns the collision from a singular event into a repeating motif. Brains repeatedly approach, collide, separate, and reset the hot phase again, with long, cool eras between brief, violent transitions. The camera could show a slow oscillation like breathing, with each exhale ending in a flash. A cyclic model must manage entropy carefully, because thermodynamics is not impressed by narrative elegance. It needs a mechanism to dilute or export disorder between cycles, or cycles quickly degrade, becoming longer, emptier, and less capable of producing structure. Entropy is the bookkeeping of irreversibility, and any cosmology that loops must explain why the books do not explode. The attraction of ekpyrosis is that it can address classic puzzles differently than inflation, while staying within a disciplined mathematical framework. It uses contraction to smooth and flatten before the bounce, rather than expansion to do the smoothing afterward. That reversal matters because it changes what initial conditions are required and when they must be set. Inflation smooths by rapid expansion that stretches irregularities away, making distant regions look similar because they were once close. Ekpyrosis smooths by a slow, ultra-stiff contraction that suppresses curvature and anisotropy, driving the universe toward uniformity as it shrinks. In both stories, the goal is the same sky we see, nearly flat, nearly uniform, but seeded with tiny variations. In technical terms, ekpyrotic matter has an equation of state with W much greater than 1, meaning pressure dominates energy density in a specific way. That makes its energy density grow faster than shear during contraction, so chaotic distortions are damped rather than amplified. In plain language, the contraction is stiff enough to keep the universe from crumpling into a lopsided mess. This changes the horizon story, which is one of the Big Bang's most famous conceptual problems. Regions can become correlated during a long pre-collision phase, without requiring a burst of exponential expansion, because the relevant scales can interact for a long time. The model tries to explain why the CMB is so uniform across the sky, even though light could not have crossed it in a naive, expanding picture. It also changes the flatness story, which concerns why spatial curvature is so close to zero today. During ekpyrotic contraction, spatial curvature becomes negligible compared to the dominant energy component, because the stiff energy grows extremely rapidly as the scale factor shrinks. The universe is driven toward flatness not by stretching, but by overwhelming any competing contribution. But the pivot comes with costs, and the costs are not just aesthetic. A contracting universe is vulnerable to mixmaster chaos unless the ekpyrotic phase is strong enough, because anisotropies can dominate in generic contractions. The phrase mixmaster refers to a class of solutions where the geometry tumbles through chaotic oscillations, a reminder that contraction is not automatically gentle. Then comes the bounce problem, which is where the story meets the stubbornness of general relativity. General relativity resists a smooth transition from contraction to expansion without violating energy conditions or adding new physics, because ordinary matter and radiation tend to focus geodesics and drive singularities. A bounce is easy to draw and hard to achieve, which is why the collision picture becomes attractive. In brain pictures, the bounce is replaced by a collision, and the singularity is traded for a higher dimensional event whose microphysics must be specified. The hope is that what looks singular in 4 dimensions is less pathological in the full geometry, because additional degrees of freedom can soften the transition. Yet the trade is not free, because one must still explain how the collision avoids infinities and produces the right particle content. The scientific question is not whether the story sounds cinematic, because cinematic stories are cheap, and the sky is not. The question is whether it reproduces the observed pattern of primordial perturbations, the tiny seeds that later become galaxies and clusters. Cosmology is constrained by statistics written in radiation, and any contender must match those numbers. Our universe's structure begins as tiny density variations, and those variations leave multiple fingerprints. The CMB shows a nearly scale-invariant spectrum with a slight tilt and near Gaussian statistics, meaning the fluctuations are close to a simple random field. The acoustic peaks in the CMB power spectrum, produced by sound waves in the primordial plasma, also lock in the physics with remarkable precision. Inflation produces that spectrum naturally from quantum fluctuations stretched outside the horizon, turning microscopic uncertainty into macroscopic structure. Ekpyrotic models must work harder to match the same data, because contraction changes how perturbations evolve and what becomes frozen in. The challenge is not philosophical, it is mathematical, and it shows up in the spectral index and higher-order correlations. In the simplest single-field ekpyrotic contraction, curvature perturbations are not automatically scale-invariant, which is a serious problem. They tend to be strongly blue, with too much power on small scales, implying a universe that would form structure too early and too violently. The model must therefore add structure, additional fields or mechanisms, to shape the perturbations into what we observe. To fix this, many ekpyrotic models use an entropic mechanism, which introduces at least 2 fields during the contraction. 2 fields generate nearly scale-invariant entropy perturbations, later converted into curvature perturbations, so the right kind of wiggles end up in the metric. Entropy perturbations are, roughly, fluctuations orthogonal to the background trajectory in field space, and they can behave differently than curvature modes. That conversion can happen near the bounce, or during a turn in field space, when the background evolution changes direction in the multi-field landscape. It is a technical step, and it introduces new parameters and new failure modes, because the timing and efficiency of conversion affect the final spectrum. If the turn is too sharp or too weak, the model can miss the data in ways that are difficult to hide. Non-Gaussianity becomes a pressure point, because it probes the interactions of the fields rather than just their linear behavior. Some ekpyrotic conversions naturally produce larger non-Gaussian signals than simple inflation predicts, especially of the local type associated with mode coupling.
In the sky, that would mean the fluctuations are not perfectly random, but slightly skewed or correlated in a specific pattern. Observations constrain non-Gaussianity tightly, using the CMB and large-scale structure surveys as statistical laboratories.
That forces ekpyrotic models into narrower corners, or toward more elaborate conversion dynamics, where cancellations or special trajectories reduce the signal. The constraints are not merely numbers on a plot. They are a way of interrogating the earliest physics without touching it. Then there is the clean discriminator that does not depend on galaxy formation details, which are messy and non-linear.
Primordial tensor modes. Gravitational waves from the earliest phase would propagate almost freely and preserve information about the energy scale and dynamics. They are ripples in space-time itself, and because they interact weakly, they are among the most pristine messengers we can hope for. Inflation generically predicts a stochastic gravitational wave background, a sea of tensor fluctuations produced by quantum effects during rapid expansion.
Its amplitude is tied to the energy scale of inflation and encoded in the tensor to scalar ratio R, which compares tensor power to scalar power. If R is large enough, it should imprint a distinctive pattern in the polarization of the CMB. Ekpyrotic contraction typically predicts very small tensor amplitudes, because the mechanism that generates scale-invariant scalars does not simultaneously boost tensors on large scales. The tensor spectrum is often blue and suppressed on CMB scales,
making R effectively tiny for the modes we can observe. In this picture, gravitational waves exist, but they hide at frequencies far from the CMB's reach. That difference becomes a test, and it is one of the few tests that feels almost binary. CMB B-mode polarization searches look for the curl pattern that primordial gravitational waves would imprint, distinct from the gradient-like E-modes produced by density perturbations.
On screen, the polarization vectors rotate into a faint whirlpool pattern, as if the sky itself were twisting.
A detection of large-scale primordial B-modes at appreciable R would strongly favor inflation-like dynamics, because it would imply a high-energy early phase that excites tensors. A continued non-detection pushes many inflation models down, while remaining consistent with ekpyrosis, which expects a quiet tensor sector. Yet the logic is asymmetric, because silence can mean many things.
But non-detection is not a clean victory for ekpyrosis, because inflation can also produce low R in many well-motivated models.
Foreground dust can mimic or hide signals, and lensing of E modes into B modes adds a confounding background that must be subtracted carefully. The sky is not a controlled experiment, and extracting a primordial whisper from galactic noise is a technical art.
So the real test is a pattern across multiple observables,
where several measurements point to the same early mechanism. The scalar tilt, running, non-Gaussianity shapes, and tensor spectrum must cohere, forming a consistent fingerprint rather than a single clue. A theory survives not by fitting one curve, but by fitting the whole forensic record. Brain collision models also invite more specific scars, because collisions are rarely perfectly clean in ordinary physics.
A collision might not be perfectly symmetric, and asymmetry could leave anisotropic imprints, like a preferred direction or a gradient across the observable universe.
The visual could show a faint directional shading across the CMB map, almost imperceptible, yet conceptually explosive. Those imprints could appear as statistical anisotropy in the CMB, meaning the fluctuations would not be identical in every direction.
They could also appear as localized features,
or unusual polarization correlations, where certain patches behave differently than the rest. The difficulty is that the universe gives us only one realization, so pattern recognition can become a mirror for our own expectations. Some scenarios predict distinctive parity-violating patterns if additional fields couple during the collision, producing correlations that would normally vanish.
Others predict oscillatory features from sharp events in the prehistory,
like a sudden change in the potential or a brief burst of interaction. Each proposed signature is a bet that the early universe left a stylized mark rather than a generic blur.
The challenge is that the CMB is already limited by cosmic variance on large scales, which is an unavoidable statistical ceiling.
Rare features can look meaningful yet be statistical flukes because we cannot rerun the universe to see what is typical. The documentary's tension lives here, in the gap between what we can measure and what we can responsibly infer. There is also the question of what counts as before, and brain cosmology forces the question to split. In these models, our brain time can begin at the collision, while bulk time continues, providing a wider ordering of events. The word before can be meaningful in the bulk, even if it is not meaningful within our four-dimensional effective description. That means before can be meaningful in the bulk, even if it is not meaningful within our four-dimensional effective description. The timeline depends on which clock you trust, and in relativity, clocks are physical objects tied to trajectories and fields. A brain observer may have a natural time coordinate that fails at the collision, while the bulk geometry still admits an extension. The bulk is not necessarily a comfortable outside, and it should not be imagined as a blank room. It is a higher dimensional space-time with its own geometry, and it can contain other brains and other histories, perhaps with different physical laws on their surfaces.
The camera could drift through the bulk like a deep ocean, with distant sheets glimmering like bioluminescent organisms.
If gravity propagates in the bulk, then the bulk is not a passive container, because gravity is geometry, and geometry back reacts. Its dynamics can influence brain motion, separation, and collision timing, altering the effective physics on the brain. In other words, the outside is not just scenery, it can push back.
Now the narrative tension sharpens into a personal kind of dread, because the model relocates our origin into a larger mechanism. If our universe is a membrane, what is outside it? And why is it there? The question feels metaphysical, yet it is also a request for boundary conditions, because physics cannot run without specifying what surrounds the system. Outside is not a place we can travel to with rockets, because rockets are made of fields that may be confined to the brain.
It is a direction in the theory's geometry,
A dimension our matter cannot explore, no matter how far we travel along the brain. The outside is not far away. It is orthogonal, like a direction you can point to but cannot step into. Yet the outside can still touch us through gravity, which may leak into the bulk and return as subtle corrections. It can also touch us through the event that may have started our hot phase, because the collision is literally an interaction with the bulk.
Even if we cannot leave, the bulk can leave fingerprints on the evolution we observe.
If collisions can happen once, they can happen again, and repetition changes fear into anticipation. A cyclic model makes that repetition a feature, and it turns impact into destiny, because the next collision is not a random accident, but part of the system's motion. The universe becomes a clockwork of approach and contact, with life living in the long intervals between strikes.
In a cyclic brain picture, the approach is slow, and the collision is brief, which creates a distinctive pacing for cosmic history.
Each cycle resets temperature and density, while the bulk persists, carrying the larger geometry through the sequence. On screen, the brains drift like tectonic plates, and the moment of contact is a thin line of blinding light. That persistence changes what the Big Bang means, because it demotes it from absolute beginning to recurring transition.
It becomes a recurring transition, not a singular beginning, and not an ultimate origin, even though it still marks the start of our observable thermal history.
The Big Bang remains special to us, but it is no longer the first page of the book. But a cyclic story must explain why cycles are stable, because stability is not guaranteed in nonlinear dynamics.
It must prevent small deviations from accumulating into runaway collapse or runaway dilution,
which would end the cycle or make it observationally irrelevant. The mathematics must show that the system has an attractor, not just a poetic loop. It must also explain why we observe a particular arrow of time, because our experience is not cyclic. Entropy must still increase locally, even if the global picture repeats, so that memories form and processes are irreversible.
The model must reconcile recurrence with the fact that we do not remember previous cycles.
and that physical systems do not spontaneously unmix. Some proposals export entropy into the bulk or into extra-dimensional degrees of freedom, treating the bulk as a sink for disorder. Others rely on accelerated expansion phases to dilute entropy between collisions, spreading it so thin that each new cycle begins effectively fresh.
These are not minor adjustments, because entropy is the difference between a viable cyclic cosmology and a thermodynamic impossibility. These moves are not cosmetic, and they are not merely patches to save a story. They determine whether the model is a viable cosmology or only a metaphor with equations, because the universe is constrained by the second law. A cyclic theory must show not only how to reset temperature, but how to reset the conditions for complexity.
There is another subtlety that matters for the central question, and it hides in the phrase, past incomplete. Even if the brain history extends earlier, the bulk itself may still be past incomplete, meaning that geodesics cannot be extended indefinitely into the past. A model can push the beginning back a layer and still face the possibility that the larger structure requires an initial boundary.
A brain collision can replace a singularity in 4 dimensions, which is a significant conceptual shift.
It does not automatically remove the need for a deeper beginning of the bulk, because the bulk may have its own singularities, boundaries, or quantum origin. The collision story can therefore be a middle layer, explaining our hot start while leaving the ultimate origin question intact. So the collision story can be a middle layer, and that layered structure echoes the documentary's hook.
If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it?
The memory here is not mystical. It is the idea that initial conditions for our hot phase may have been set by a prior dynamical era. In brain cosmology, the memory could be literal boundary conditions from a pre-collision phase, encoded in the spectrum and statistics of perturbations.
The CMB becomes a forensic record of an impact, like a crater pattern that reveals the angle and speed of a collision.
We do not see the brains directly, but we might see the statistical residue of their motion. But the record is hard to read, because different early universe mechanisms can produce similar scalar spectra. Many different early universe mechanisms can produce similar scalar spectra, and the universe gives us only one sky, one dataset, one chance.
This is why cosmology often feels like archaeology conducted with photons, where interpretation must be cautious.
So we return to what can discriminate, and the list is short but powerful. Tensor modes are one lever, and non-Gaussianity shapes are another lever, because they probe different aspects of the underlying dynamics. If the universe is hiding its origin behind a veil of near-scale invariance, we must look for the weave.
A third lever is anisotropy, because a collision could define a preferred direction in a way that standard cosmology tries hard to avoid.
A collision could define a preferred direction, and that would violate the near isotropy that standard cosmology assumes, even if only slightly. The cosmological principle is an empirical generalization, not a law, and a collision would test its limits.
Observations show the universe is remarkably isotropic, with only small anomalies debated at low significance.
Any collision imprint must be subtle or rare, or else it would already have been obvious in the CMB maps. That subtlety is itself a constraint, because a violent event must somehow leave a gentle statistical trace. Even subtle imprints matter, because they would change the emotional meaning of origin without changing the night sky's beauty.
Our beginning would be an accident of higher dimensional motion, a consequence of trajectories in a space we cannot inhabit.
The universe would feel less like a singular miracle and more like one outcome among many possible contacts. The terror is not only that we are not central, which modern cosmology has already taught us repeatedly. It is that our existence could be collateral damage from dynamics we cannot see, driven by fields and geometries that never appear in our laboratories.
The brain picture replaces a singular beginning with a larger indifference, and that can feel colder.
If our brain is one surface among many, then the bulk may be crowded, even if it is inaccessible. Other brains could carry other universes, separated by dimensions rather than distance, like parallel pages in a book that never touch, until they do. The thought is not that we can visit them, but that their presence could be part of the same underlying structure.
A collision could be a one-time catastrophe or a repeating heartbeat, and the difference is existential. Either way, it makes the cosmos feel mechanical and indifferent, because the event that defines our origin becomes a generic process. The Big Bang becomes less like a sacred beginning and more like a phase change in a larger system. And yet the idea is not pure speculation, because it is tied to attempts at quantum gravity and to technical necessities in candidate theories. It is tied to attempts at quantum gravity and to the fact that our best theories hint at extra structure, even when we try to avoid it. The brain is not introduced to solve a storytelling problem. It is introduced because certain mathematical frameworks naturally contain such objects. String theory is not confirmed, but it is a serious attempt to unify quantum mechanics and gravity, and it has generated tools that have influenced physics broadly. Brains are not optional in that framework. They are central objects, carrying charges and hosting gauge fields in many constructions. Even if nature does not choose string theory, the conceptual move, geometry plus extended objects, has reshaped how physicists imagine fundamental structure. Ekpyrotic models are not the default cosmology, but they are a disciplined alternative, built to be testable rather than merely evocative. They show that inflation is not the only way to address early universe puzzles, even if inflation remains the most widely used framework. The value is partly philosophical. Multiple consistent stories prevent complacency, and partly practical, because alternative predictions sharpen what we should measure. So the Big Bang becomes a frontier again, a boundary of our effective description rather than an unquestionable origin. It is the point where our effective four-dimensional description begins, not necessarily where reality begins, and that distinction is the chapter's core. The frontier is real because our equations and observations have limits, yet the frontier may not be the edge of existence. Now we narrow the meaning of before one more time, because the word has been doing too much work. Before can mean earlier along our brain time, earlier along bulk time, or earlier in a deeper ordering that does not map cleanly onto either. Each meaning implies a different kind of explanation, and each demands a different kind of evidence. If bulk time exists, then the question becomes sharper, not softer, because we have merely moved the mystery outward. What sets the bulk's initial conditions, and why does the bulk exist at all? A larger stage does not eliminate the need for a first cue, unless the stage is itself eternal or self-contained. If bulk time does not have a first moment, then the collision is not an origin, and that changes the philosophical weight of the Big Bang. It is a transition inside an eternal or self-contained structure, where beginning is a local feature rather than a global one. The Big Bang would be like dawn on a planet, real, dramatic and bounded, yet not the beginning of time. That brings us to the next pivot. What if even the bulk has no first moment, and what if time itself had no beginning? The question is unsettling because it suggests that the deepest layer may not be a longer timeline, but a different concept altogether. We carry the central question forward because the collision does not end it, and it does not even answer it completely. It only relocates it to a larger stage we barely understand, where our usual intuitions about clocks and causality may fail. The Big Bang may not be a first moment, but a frontier, and the frontier might be a bruise on a brain, inside a reality with no start. The transition is simple and unsettling, because it points beyond geometry into the nature of time itself. If time can exist outside our universe, then time might also be an illusion inside it, emergent from deeper relationships rather than fundamental. Next, we follow the question past collisions and bulks. We ask whether time is fundamental, or whether it is something that emerges and can disappear. Chapter 4 ended by pushing the mystery outward, from our hot beginning to time itself. If the Big Bang is a frontier, then before may be the wrong question.
We ask the central question again, but we change its grammar and its assumptions. Did anything exist before the Big Bang? And if time began there, what could before even mean? Everyday language treats time like a container that events sit inside, like water filling a glass.
We picture moments stacked in order, each one waiting patiently for the next. That picture is useful for calendars and memory, and it matches the way our brains sequence cause and effect. Yet it quietly smuggles in a background clock that ticks the same everywhere, regardless of motion or gravity. Modern physics, however, treats time as part of the system, shaped by energy and motion. Time is not merely a stage, it is part of the script. In general relativity, time is stitched to space into space-time, a four-dimensional fabric that can bend. Matter and radiation tell space-time how to curve, and that curvature tells matter how to move. Visually, it is less like a rigid grid and more like a flexible sheet, dimpled and stretched by whatever it contains. Near massive bodies, the dimples deepen, and the paths of light and clocks tilt in response.
The geometry evolves, and clocks measure paths through that geometry rather than ticking in isolation. A clock is not a universal referee. It is a physical object tracing a world line. That world line is a history written in space-time, and different histories can accumulate different amounts of time. Two identical clocks can disagree after following different routes, because time is a measure of space-time distance, not an external metronome. So, before the Big Bang quietly assumes a background clock that keeps ticking behind the scenes. But the Big Bang may be where that clock stops being defined, because the notion of a smooth time coordinate breaks down. In the standard Big Bang model, the phrase t equals 0 is not a filmed instant waiting to be replayed. It is a limit of an equation, and limits can signal missing physics rather than a literal beginning.
When cosmologists say the universe was hotter and denser in the past, they mean something precise. They mean the scale factor was smaller, and the energy density in radiation and matter was higher. The scale factor is a bookkeeping device for cosmic size, and it translates directly into redshift. As space expands, wavelengths stretch with it, so ancient light arrives thinned into longer, redder waves. Run the equations backward and the temperature rises. The wavelengths of light shorten and the plasma becomes more tightly coupled. Yet that mathematical extrapolation may be pointing toward a boundary of the model, not a literal first frame. In that early plasma, photons scattered constantly off free electrons, and matter and radiation behaved like a single fluid. Pressure waves traveled through it, leaving oscillations that later became the CMB's acoustic peaks.
Cosmology still tempts us with a simple alternative, one that feels almost like relief.
Maybe the clock never started, because time extends indefinitely into the past. A past eternal universe sounds like a way to dissolve the origin problem. If there is no first moment, there is no need for a first cause. But past eternal does not mean static or unchanging, and it does not mean calm. It means the timeline has no earliest page, even if chapters begin, end, and restart.
The idea has a long history, because it is as old as the discomfort with beginnings.
Ancient philosophers argued over whether the cosmos had an origin, and modern cosmology inherited that unease in mathematical form. Aristotle favored an eternal cosmos, while other traditions insisted on a definite beginning, and the tension never fully disappeared. When Einstein's equations arrived, they turned the argument into geometry, forcing expansion or contraction unless special conditions were imposed.
We begin with the intuition behind steady-state thinking, updated for modern data and modern humility.
The universe could be eternal, yet locally evolving, if creation or transitions keep it looking similar on large scales. In the mid-20th century, the steady-state model offered a striking promise. As the universe expanded, matter would be continuously created, keeping the average density constant and the cosmos statistically unchanged.
It was elegant in one sense, because it made the universe the same at all times. It also carried a philosophical charge. The universe would have no special moment of birth.
The model leaned on what was called the perfect cosmological principle, extending uniformity not just across space, but across time. That extension was audacious, and for a moment it felt like a clean escape from cosmic origin stories. Classic steady state failed because the universe changes with redshift, and the sky keeps receipts. The cosmic microwave background, discovered in 1965, is not a minor detail. It is a relic radiation field with a near-perfect black-body spectrum. A black-body spectrum is a thermal fingerprint, and it is hard to counterfeit by late-time astrophysics. Its smooth curve tells us the radiation once equilibrated in a hot, dense environment, then cooled as space expanded. The CMB and galaxy evolution show a hot, dense past, and they show it quantitatively. When we look farther away, we look back in time, and we see younger galaxies, different star formation rates, and a universe that does not resemble the present. Radio surveys, quasar counts, and the abundance of galaxy clusters all shift with distance in a way steady state could not absorb. The universe has a history written into its populations, and that history points toward a hotter, simpler past.
Yet the deeper impulse survives in newer models, because the desire for an eternal past never truly left.
Replace continuous creation with phases, bounces, or an emergent prehistory, and the old question returns wearing new mathematics. One family is the emergent universe scenario, which tries to keep the past without keeping the old steady-state machinery. The cosmos exists for an arbitrarily long time in a quasi-static state, then transitions into inflation. In these models, the scale factor can hover near constant for ages, neither collapsing nor expanding rapidly. The universe is not empty in this phase, but it behaves as if it is balanced on a knife edge. Imagine a wide, dim cosmic landscape, almost motionless, where the horizon does not race outward and distances barely change. The stillness is not death, though. It is a poised configuration, waiting for the slightest push.
Then a trigger destabilizes the state, and rapid expansion begins, smoothing and stretching space.
The transition is meant to be graceful, like a quiet room suddenly filling with wind. The appeal is surgical, because it targets the origin problem without discarding the successes of the hot Big Bang picture. You keep an eternal past, but you still generate a hot Big Bang-like phase after inflation and reheating.
Reheating matters here because inflation by itself is cold and sparse in many models.
The energy stored in the inflationary field must be converted into particles and radiation, repopulating the universe with a thermal bath. That conversion is not just a narrative flourish, because it sets the initial conditions for everything that follows. It determines how many photons exist per baryon, how quickly the plasma thermalizes, and whether later nuclear reactions have the right starting point.
That thermal bath is not an aesthetic preference. It is demanded by what we see.
The early universe must be hot enough for nuclear reactions, and it must cool at the right rate for those reactions to freeze out. The danger is also surgical, because the quasi-static eternal state can be unstable in subtle ways. Small perturbations can ruin the long calm, and quantum fluctuations can accumulate over an arbitrarily long duration.
An eternal plateau is a demanding thing to build, because almost stable is not stable when given infinite time. Even tiny departures can grow, and the model must explain why they do not. In practice, stability means controlling both classical modes that can drift and quantum modes that can seed runaway behavior. Over limitless time, even low-probability excursions become practically guaranteed unless a mechanism suppresses them with unusual strength. To be viable, the model must also reproduce what we actually observe, not merely what we can imagine.
It must deliver near-flat geometry, the CMB spectrum, and the seeds of structure that later become galaxies. Flatness is not optional, because observations constrain spatial curvature tightly across multiple probes. The universe looks very close to Euclidean on large scales, with curvature so small that it is difficult to detect.
In the language of cosmology, that means omega is extremely close to 1 today.
Any past eternal history must still land near that value, not by accident, but by a mechanism that makes it natural. Structure is not optional either, because galaxies require primordial perturbations. Those perturbations must have the right statistical properties, nearly scale invariant, slightly tilted, and close to Gaussian. Scale invariant means fluctuations are similar across a wide range of sizes, with only a gentle preference. The tilt is measured precisely in the CMB, and it is one of the sharpest tests for early universe physics. The CMB is the forensic record that keeps every theory honest, because it is a snapshot of the universe when it was about 380,000 years old. At that moment, electrons and protons combined into neutral atoms, and light finally traveled freely.
Before that, the universe was a glowing fog, and photons could not travel far without scattering. After recombination, the fog cleared, and the radiation streamed outward, carrying a frozen image of the plasma's last vibrations. That light has been stretched by expansion into microwaves, and it still fills the sky. Its tiny temperature variations, tens of microkelvin, encode the acoustic history of the primordial plasma.
Any prehistory must feed into the same acoustic peaks and polarization patterns we measure today. Those peaks are not decorative. They are the harmonics of sound waves in the early universe, frozen into radiation. Polarization adds another layer of testimony, because it records the directionality of scattering at last contact. It is like a faint grain in a photograph, and it constrains how perturbations were arranged long before atoms formed. Now the suspense tightens, because inflation itself seems to resist an eternal past. A theorem enters the story, and it is often misunderstood. The Borde-Guth-Vilenkin theorem is not a model, and it is not a guess. It is a general statement about many expanding spacetimes, derived with minimal assumptions compared to any specific inflationary scenario. The accessible version is simple, but it hides careful reasoning.
If the average expansion rate along a past-directed world line is positive, that world line cannot be extended indefinitely backward. The theorem uses geodesics, the paths that free-falling observers follow when no forces act on them. In curved spacetime, a geodesic is the closest thing to a straight line, and it is how relativity encodes inertia. It asks whether those paths can be continued forever into the past, or whether they hit an edge. The edge is not necessarily a wall of infinite density. It is a limit where the classical description stops making sense. Past incomplete means there is a boundary to the extension, a place where the geodesic cannot be continued. It does not necessarily mean a singularity with infinite curvature, but it means the spacetime, as described, is not past eternal. A useful visual is a line on a map that simply ends, not because the traveler crashed, but because the paper runs out. The theorem says many inflating maps run out in the past, even if they sprawl endlessly forward. In practice, BGV targets inflationary spacetimes and other eternally expanding histories. If expansion is positive on average, the past is not complete, even if the future can continue forever. That sounds like a verdict against past eternal inflation, and it is often quoted that way. It suggests inflation cannot be the whole story, even if it is eternal to the future and endlessly spawns new regions. But the theorem is not the end of the debate, because it has assumptions that can be questioned. It assumes a classical space-time description and a certain notion of expansion defined along geodesics. Classical space-time is a powerful approximation, yet we already know it cannot be the final word. Near the Planck scale, quantum effects are expected to become dominant, and the smooth manifold picture may fail. At those energies, the very idea of a sharply defined metric may blur, and fluctuations could be as important as averages. If geometry becomes probabilistic, then extend the geodesic may be as ill-posed as extending a path through a cloud. Quantum gravity may change what a geodesic even means, because path and distance may not be fundamental. If space-time is emergent from deeper degrees of freedom, then incompleteness of classical paths may not imply a true beginning.
BGV also does not say what replaces the incomplete region, and it does not pretend to. It only says the inflating phase cannot be extended indefinitely backward as it stands, which is a constraint, not a full narrative. So the theorem becomes a pressure point, not a final answer. And pressure points are where theories reveal their hidden costs.
It forces any past eternal model to explain what the earlier layer really is and how it avoids average expansion. Some proposals answer by adding a pre-inflationary phase with different behavior, such as a quasi-static regime. Others answer by denying that classical time exists at the deepest level, so the question of extension becomes misplaced. Either way, the word before becomes slippery, and that slipperiness is not merely linguistic. It is a sign that our conceptual tools may be tuned to everyday scales, not to the birth or non-birth of a universe. Now thermodynamics enters, because time is not only geometry and coordinates. Time has an arrow, and the arrow is written in entropy. Entropy measures the number of microscopic arrangements compatible with what we see at the macroscopic level. In plain terms, it counts how many hidden configurations could underlie the same visible state. The second law says entropy tends to increase in closed systems because there are more disordered arrangements than ordered ones. That tends is statistical rather than absolute, but the statistics are overwhelming for large systems. Our universe has a strong arrow of time, and it shows up everywhere we look. Stars burn fuel, structures form and heat spreads, and the bookkeeping never reverses on its own. Even gravity participates in the story in a counterintuitive way. While gas in a box spreads out, matter under gravity can clump, forming galaxies and stars, yet the total entropy still increases through radiation and complex microstates. Gravitational systems can increase entropy by creating contrasts, hot stars and cold space, dense cores and diffuse halos, because those contrasts open up more microscopic possibilities. Black holes push this to an extreme, acting as enormous entropy reservoirs in a compact form. A past eternal universe seems to threaten that arrow, and it does so with a simple question. If it has existed forever, why is entropy not already maximized everywhere? This is the heat death worry, sharpened into a cosmological constraint rather than a philosophical mood. In many systems, given enough time, the most probable state is thermal equilibrium, with no free energy left to do work. An eternal past seems to imply an already exhausted universe, a cosmos that has run out the clock. If equilibrium is the destination, then infinite time behind us suggests we should already be there. There are ways to respond, but each response has a cost that must be paid in dynamics or assumptions. You can allow entropy to grow without bound, or you can export it to new degrees of freedom that keep the local universe young. Inflation can dilute entropy locally by stretching space and smoothing gradients, and that can reset conditions in a region. But dilution is not deletion, and the global accounting still matters if the whole space-time is considered. Cyclic models face the same bookkeeping problem in a different costume, because repetition accumulates baggage. Without an entropy management mechanism, cycles degrade, the maximum grows, and the past becomes implausible rather than infinite. Some scenarios propose that the arrow of time is local and emergent, not a single global direction stamped onto everything. The global state could be time-symmetric, while subsystems experience a one-way flow because of boundary conditions and correlations. That move changes what initial condition means, and it changes what counts as an explanation. The low-entropy past might be replaced by a dynamical selection mechanism, not a special starting moment chosen by hand. Yet the discomfort remains, because mechanisms must be specified, and they must be consistent with known physics. If entropy is exported, where does it go? And why does it not come back? Now we pivot from cosmological history to the nature of time itself, because the deepest escape from before is to question time's fundamentality. The most unsettling possibility is that time is not fundamental. Emergent time says the universe at bottom may be timeless, described by relations rather than evolution.
What we call time arises from correlations between parts of the system, like a pattern that appears only when you zoom out. In this view, change is not measured against an external clock that exists independently. Change is relational, tracked by one subsystem serving as a clock for another, because some degrees of freedom can act as reliable reference variables. A pendulum, an atomic transition, a vibrating crystal. Each is a physical process that can label other processes.
The key point is that the label is internal to the universe, not imposed from outside. Quantum entanglement becomes more than a weird feature in this context. It becomes a candidate ingredient for why time appears to flow in complex systems, because entanglement structures correlations that can mimic causal order. When entanglement spreads, information becomes distributed, and reversing the distribution becomes fantastically difficult in practice. That practical irreversibility can line up with the thermodynamic arrow, making time's direction feel like a physical gradient. The idea is not that time is fake in daily life or that experiences are illusions. The idea is that time is approximate, like temperature, real for subsystems and coarse-grained descriptions, but not necessarily written into the deepest equations. Temperature is a useful analogy because it depends on averaging over many microscopic states.
A single molecule does not have a temperature in the same way, yet a gas does, and the concept becomes predictive at the right scale. This connects to quantum cosmology, where the universe is treated as a quantum system with no outside observer. In that setting, the usual time parameter becomes slippery, because there is no external clock to compare against. A famous hint is the Wheeler-DeWitt equation, which arises in canonical approaches to quantum gravity. In a simplified form, it sets a constraint on the universe's wave function without an explicit time variable. This is sometimes called the frozen formalism, and the phrase is meant to sting. The fundamental equation looks static, as if the universe's state does not evolve, even though everything we know seems to involve change. Yet we clearly experience evolution, and physics describes processes that unfold.
So the question becomes technical and existential at the same time. How does time reappear inside a timeless equation? One answer uses internal time, which is less mystical than it sounds. You pick a degree of freedom, like a scale factor or a field, and treat it as a clock relative to others. Then dynamics becomes conditional rather than absolute, and the language shifts subtly.
Other variables change with respect to that internal clock, even if the full wave function satisfies a timeless constraint. In practice, this can look like recovering a Schrödinger-like evolution for subsystems, under approximations that separate clock variables from system variables. The emergence is not free, because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free, because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free, because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on semiclassical regimes and well-behaved correlations. The emergence is not free because it depends on summer-classical regimes and well-behaved correlations. The emergence is not free because it depends on summer-classical regimes and well-behaved correlations. The emergence is not free because it depends on summer-classical regimes and well-behaved correlations. The emergence is not free because it depends on summer-classical regimes and well-behaved correlations. The most for the completely, because they realized in eternal earth, the clos keeps of completely before them. The trementing cum fact that could return that the result previous to do that. It was biggest appointment of the regerb in clause. The time and seems like that, we other things that we will get it descripted. The general law then, we have the components is the plat. It is a very recent with internal clock. The result we will get enough to properly that we will do. The time and realized we will be. The emergence is not free because it depends on summer-classical regimes and well-behaved correlations. The trementing trum fact that could return that the result previous to do that. The presenting trum fact that we will do. The trementing trum fact that we will get a descripted for the more. Because they will doing sown as well it did. The cross the live that the result previous to do that. The result we will get a descripted for the more. Because they will doing sown as well it did. The only reach of mental clock, because they will be concerned that we will do. The result we will get a descripted for the more, because they will doing sown as well it did. The tracting we will do in the trementing from fact, the most probably increase to do that. The tracting we will do the trementing from fact, we open to work interest that the result previous to do that. The trementing to get a the more than force that means we will get a descripted for the more, because they will doing sown as well it did. The trementing from fact that we will do was completely difficult. The trementing from fact that we will do that the result previous to do that. The trementing from fact that we will do that the result previous to do that. The trementing to get a the more than force that means we will do that the result previous to do that. The trementing like a lot because they will do that the result previous to do that. The trementing to get a the more than force that means we will do that the result previous to do that. The trementing from fact that we will do that the result previous to do that. The trementing from fact that we will do that the result previous to do that. Emitting the more, but we will do that the result previous to do that. This intimate of life, we she do that the result previous to do that. The trementing to get a the more, but we will do that the result previous to do that. The emergence is not free, because they will do that the result previous to do that. The most period of journal to the tractig, they will get for the most and addition for the tract. The result previous to do that in created with the computer. The result previous to do that in places. The emergence is not free, because they will do that the result previous to do that. The result previous to do that is not to deeped clock. The presenting of everyone, we have to follow that the result previous to do that. The result previous to do that is more but the most previous to do that in created. The result previous to do that in created. The result previous to do that in created with the computer. The result previous to do that in created with the presenting. The result previous to do that in created with the computer. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. The result previous to do that in created with the presenting. Behaved correlations. This does not solve everything, because the choice of clock can be ambiguous, and ambiguity matters near extremes. Different choices can yield different notions of time, especially near regimes where classical geometry is not a good guide. But it shows how before might be a category error rather than a missing fact. If fundamental reality is timeless, then asking what happened before is like asking what is north of the North Pole. The analogy is not meant to evade curiosity, but to redirect it. North of the North Pole is not a hidden continent. It is a misuse of coordinates, and before time may be similar. Now the chapter loops back to observational discipline, because even radical ideas must cash out in measurable consequences. Even if time is emergent, our effective description must match the data in the regime we can test. The expansion history matters because it is measured rather than imagined. Supernovae provide standardizable candles. Baryon acoustic oscillations provide a standard ruler, and the CMB anchors the early time boundary of the thermal story. These measurements constrain how the scale factor evolved, and they constrain the contents of the universe. They tell us about dark energy's late-time dominance, matter's earlier control, and radiation's ancient reign. The early universe must still produce the observed light element abundances, and that requirement is unforgiving. Big Bang nucleosynthesis ties the hot phase to specific temperatures, densities, and expansion rates within the first few minutes. Hydrogen, helium, and traces of deuterium and lithium are not just chemical facts. They are fossils of a nuclear epoch, and their abundances depend sensitively on how quickly the universe expanded while reactions were still occurring. Deuterium is especially revealing because it is easily destroyed inside stars and not easily made later in large quantities. Its measured abundance acts like a cosmic thermometer, pointing back to a narrow window of conditions in the early fire. Any past eternal or emergent time model must reproduce this thermal track, at least effectively. It must also explain why the CMB is so uniform yet not perfectly smooth, because the imperfections are where structure begins. Uniformity is the horizon problem in its familiar form, and it is not merely a rhetorical puzzle.
Regions of the CMB sky were not in causal contact in a simple hot Big Bang extrapolation, yet they share nearly the same temperature. Inflation addresses this by stretching a once-connected patch to cosmic size, and many alternatives must replicate that success. If a prehistory is invoked, it must still explain why the universe looks like it was smoothed. Curvature constraints are especially unforgiving, because curvature does not hide easily. The universe appears very close to spatially flat, and that fact is a boundary condition any theory must earn rather than assume. So the story becomes a balancing act, and the balance is delicate. You want no beginning, but you must still deliver the same sky, the same structures, and the same statistical fingerprints. Now we return to BGV with a sharper lens, because it sits at the intersection of geometry and narrative.
If many expanding spacetimes are past incomplete, then an eternal past requires either non-expanding averages or new physics. A quasi-static emergent phase tries to keep the average expansion near zero in the deep past. That can evade the theorem's condition, but it must remain stable against classical perturbations and quantum fluctuations. Stability here is not a vague preference, because an eternal phase must endure every small disturbance.
The longer the phase lasts, the more opportunities there are for rare events to occur,
and rare events become infinite time. A quantum gravity phase tries a different evasion, and it is more radical in its implications. It denies that classical space-time exists far enough back for BGV's assumptions to apply, so past-directed geodesic is no longer the right tool. Either way, the suspense is real, because each escape route changes what we mean by explanation.
The universe seems to resist both a clean beginning and a clean eternity.
If there is a beginning, we face a boundary where explanation stops, at least in its usual form. If there is no beginning, we face an infinite regress with no first link, and the demand for a starting point goes unsatisfied. A chain with no first link is logically possible, but it feels hostile to intuition and to storytelling.
It forces us to ask what counts as an explanation in physics, and whether explanation must always terminate.
In a past eternal picture, every event has earlier causes, but there is no initial cause to ground the sequence. The universe becomes a story with no opening scene, only an endless middle. That is the unsettling implication of this chapter's title, and it is meant literally. Time itself had no beginning, and the demand for an origin may be a human reflex rather than a physical necessity.
Yet the terror is not only philosophical, because our tools are built around initial value problems and boundary conditions.
We solve equations by specifying a state at one time and evolving it, and that method is woven into the practice of physics. Physics often predicts by specifying a state at one time and evolving it forward, because that is how differential equations behave. If there is no first time, the usual setup becomes less natural, and the question becomes what replaces it.
Some approaches replace initial conditions with consistency conditions,
shifting the burden from a starting moment to a global constraint. The universe is constrained as a whole, and local histories must fit the whole, like pieces of a single puzzle. That can feel like trading a beginning for a rule, and the trade is not obviously an improvement. But it also risks making the universe feel like a self-contained object, not a process unfolding, even though our experience is process.
Now we tighten the hook that has followed every chapter, because the observational universe seems to carry a strange kind of memory. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? In this chapter, the memory could be the opposite of a beginning, and that reversal is part of the unease. It could be the imprint of a long prehistory, or the shadow of timeless laws that funnel many histories into the same outcome. The CMB's simplicity could be the residue of a smoothing mechanism that operated for an arbitrarily long time,
ironing out irregularities before the hot phase. Or it could be the generic outcome of an attractor in a deeper theory, where many initial states converge.
An attractor is a dynamical tendency, a basin that pulls different starting points toward the same behavior. In plain terms, it is a cosmic habit, and habits can masquerade as memories.
But the same data can be read in multiple ways, and that ambiguity is part of the dread. We may be staring at clues that do not uniquely point backward, because different prehistories can leave similar effective signatures. Even the language of initial conditions may be misleading if time is emergent. What looks like an initial state could be a boundary in a higher dimensional description, or a condition on correlations rather than a moment in time.
We end with a pivot that changes the stakes again, because the nature of time determines the nature of the present.
If time is emergent or illusory, then the present may not be a moving point. If the flow of time is not fundamental, then now might be a perspective inside a larger structure, a slice through a more complete description. The next chapter asks the forbidden follow-up, because it takes the idea to its coldest conclusion.
If every moment is equally real in the underlying description, could the universe exist all at once? Could the terror be not an endless past, but a frozen totality? We carry the central question forward, now sharpened by doubt about the clock itself. Did anything exist before the Big Bang? And if time began there, what could before even mean? The Big Bang may not be a first moment, but a frontier, and frontiers are where maps fail.
The frontier may be where time, cause, and explanation stop behaving like we expect, even if the sky still looks calm. Chapter 5 ended by doubting the clock itself, and that doubt changes everything we thought was stable. If time is not fundamental, then the present may not be a moving point at all. The familiar sensation of now could be a local effect like warmth, real to us, but not written into the universe's base layer. We return to the central question with a colder grammar, stripped of comforting verbs like began and then. Did anything exist before the Big Bang? And if time began there, what could before even mean? The question sounds simple, yet it hides an assumption that reality must be arranged in a single queue, waiting its turn to exist. This chapter shifts from cosmology's origin stories to time's structure, because structure is where the paradox hardens. The terror is not an earlier universe hiding behind a curtain. The terror is a universe that never becomes, because becoming was never part of the design. Einstein's relativity is where the trap first closes, and it closes with equations that have been tested for more than a century. It does not merely say clocks run differently when they move or sit in gravity. It says the idea of a single shared now fails, not as poetry, but as geometry. In everyday life, we assume simultaneity is universal, and we build our language on that assumption. We assume distant events can be labeled as happening at the same time everywhere, as if the universe carries a master timestamp. When you look up at the moon, you feel as if you and the moon share a present moment. That feeling is practical, and it is usually harmless, because our speeds are slow and our distances are small. Special relativity breaks that assumption with a technical, testable claim that begins with light. Simultaneity depends on the observer's motion, because light speed is invariant in vacuum for all inertial observers. That invariance is not a philosophical preference. It is a measured fact, confirmed by experiments from Michelson and Morley onward, and refined by modern particle accelerators and satellite clocks. If light speed is the same for all inertial observers, then time and space must mix, because something else must give. Different observers disagree on which spatially separated events are simultaneous, even when each uses careful procedures and ideal instruments. The disagreement is not because one observer is confused. The disagreement is because, at the same time, is not a universal relation across space. That disagreement is not about measurement error or slow signals, and it does not vanish if you build better clocks. It is built into the geometry of space-time, and it survives every correction you might try to apply. Even if you imagine perfect synchronization, the rule for synchronizing clocks already depends on motion. The method itself carries the seed of the conflict.
We can make it concrete with an accessible example that is simple enough to visualize. Two observers pass each other, each carrying a synchronized set of clocks that were calibrated in their own rest frame. Picture two long trains sliding past on parallel tracks at a significant fraction of light speed. Each train has identical clocks mounted along its length, and each crew has used light signals to synchronize them. One observer defines a slice of now across space, using their own synchronization procedure, and that slice is a flat plane through space-time. The other observer, moving relative to the first, defines a different slice that tilts because their time axis is rotated in Minkowski geometry. In a diagram, the difference looks like a fan opening. In lived experience, it looks like a disagreement about what exists right now, far away. An event that is already happening for one observer can be not yet happening for the other, even if both are honest and careful. Neither observer is privileged by the laws of physics, because Lorentz symmetry treats inertial motion as relative. This is the relativity of simultaneity, and it is the first hint of a block universe. If there is no universal present, then the present is not a place the universe can point to. Relativity replaces the old picture of time as a river with a four-dimensional structure that does not need a current. Events are points in space-time, not beads on a single global string. The word event here is precise. It means something with a location in space and a location in time, like a flash, a collision, or a heartbeat. Once you accept events as the basic units, the temptation to imagine a universal now begins to look like a leftover habit. In Minkowski spacetime, the interval between events is what remains invariant, even when observers disagree about distances and durations. Space and time coordinates change with motion, but space-time distance does not, and that is the anchor. The interval is built from the metric, which combines time and space with opposite signs. In plain language, it is the quantity nature preserves when you change frames. The space-time interval divides separations into time-like, light-like, and space-like. And that division is more than a classification. It is the boundary between what can be connected by cause and effect and what cannot. Time-like separation means one event can be reached from the other by something moving slower than light. Light-like separation means only light, or anything massless, can connect them. Space-like separation means no influence can travel between them without breaking relativity's speed limit. Light cones encode causality in geometry, and they are among the most visually powerful ideas in physics. The future light cone contains events you can affect because signals from you can reach them. The past light cone contains events that can affect you because signals from them can reach you. When you look at a star, you are not seeing the star as it is now. You are seeing a point on your past light cone, a piece of the star's world line that intersects your present. Events outside the light cone are space-like separated, and the prohibition is absolute within relativity. No signal traveling at or below light speed can connect them, so causal influence is forbidden. You can still draw a line between them on paper, but physics will not let that line carry information. This is why relativity is not merely about clocks. It is a theory about what relationships between events are even allowed. Relativity gives us a strict causal order for some pairs of events, and that order does not depend on who is watching. If one event is inside another's future light cone, all observers agree on the order, because the interval is time-like. But for space-like separated events, there is no observer-independent order, and the math makes that unavoidable. Different observers can legitimately reverse which event happens first, because first is not a frame-free label there. That is the key pressure point, and it presses directly against our intuition about a flowing present. If the universe had a single moving now, it would need a universal ordering of all events, including space-like one. Relativity refuses to provide that ordering, because it would contradict the symmetry that keeps light speed invariant. It gives a partial order tied to light cones, and it leaves the rest dependent on perspective. From this, eternalism becomes a natural interpretation, not because it is comforting, but because it is economical. Space-time is a four-dimensional block where all events exist, and now is a slicing choice made by an observer.
In the block universe, the past is not gone and the future is not unreal.
Past, present, and future are equally part of the space-time manifold, even if we only ever inhabit a thin thread of it. The sensation of flow becomes an emergent feature of observers inside the block, and emergence is a familiar pattern in physics.
Temperature emerges from molecular motion, even though no single molecule contains temperature. In the same way, the feeling of time's passage may emerge from how brains and bodies process change. Consciousness tracks change along a world line and calls that tracking time. Your life becomes a world line, a continuous path through space-time that can be drawn like a curve. Each point on that path is an event, and the whole path exists as a geometric object in the theory.
In a visual sequence, we might see a newborn's first breath, a child's first step, and an old hand closing. Each moment pinned like a coordinate, not washed away by a current. This is not a claim that physics proves eternalism uniquely, and it is important to keep that humility. It is a claim that relativity makes presentism costly, because presentism demands a hidden preferred frame.
A preferred frame would restore a universal now, but it would be extra structure layered on top of the equations. It would need to be undetectable, or else it would contradict relativity's symmetry, which has survived every precision test. Historically, this shift was not immediate because even Einstein wrestled with the implications. Minkowski's 1908 reformulation, space by itself and time by itself are doomed to fade away, was not just rhetoric. It was a declaration that the mathematics had changed what real could mean. The block universe reading is one way of taking Minkowski seriously, and it is difficult to unsee once you do. Some theories allow preferred foliations, especially in quantum contexts where measurement feels like an intrusion. But the elegance of relativity is that it works without them, and the data supports it. The block picture fits the mathematics with fewer add-ons, and physicists are trained to distrust unnecessary structure. Space-time is the arena and the record does not rewrite itself. We can underline the example again because it is the chapter's hinge and the viewer's anchor. Two observers in relative motion disagree about distant simultaneity, so no universal present exists. If no universal present exists, then the present cannot be the boundary between real and unreal. The boundary becomes observer-dependent, which reality resists, because reality does not seem to change when you change your speed. This is where the chapter becomes the climax, because the implication is not abstract. The Big Bang, your birth, and the end of the universe may be equally real, separated only by geometry. The difference is not existence. The difference is location in space-time, and location is not a moral category. In standard cosmology, we often speak as if the Big Bang happened and then vanished, like a match struck in darkness.
In a block view, it is not a disappearing moment. It is a region, a domain of extreme density and temperature that sits at one end of many world lines. When we say the universe was once hot and dense, we are pointing to a part of the manifold, not to something that has ceased to be.
Many cosmological models represent the Big Bang as a boundary or hypersurface in space-time, and that language matters.
It is a limit of our classical description, not necessarily a literal edge of existence. General relativity predicts singular behavior when densities diverge, but singularities often mark the failure of a model, not a confirmed physical object. The boundary is where our equations stop being trustworthy, and where deeper physics is expected to take over.
In an expanding universe, we label time by cosmic time, tied to the average motion of matter and radiation.
That coordinate is useful because it matches the large-scale symmetry we observe. But it is not the universe's master clock, and it is not guaranteed to be fundamental. Cosmic time defines a convenient foliation for co-moving observers, those who ride with the Hubble flow.
Cosmic time makes the universe look like it has a shared age,
and that is why it appears in textbooks and documentaries. Yet it is a symmetry-based choice, not a metaphysical decree. Relativity allows many foliations, many ways to slice space-time into space at a time. The physics does not single out one slicing as the true present, even if one slicing is especially convenient for cosmology.
So the Big Bang can be treated as a boundary in one foliation, while another slicing intersects it differently. The geometry stays, while the storytelling changes, and that is a disorienting lesson. It suggests that some of our deepest narratives are coordinate-dependent. The universe remains what it is, while our descriptions rotate around it. This reframes the central question without answering it in the usual way, and the reframing is the point.
If the Big Bang is a region in a block, then before is not a universal direction. Before becomes a relation between events along world lines, not a global label stamped on the cosmos. The question becomes, which events are in the past light cone of which observers, and whether space-time extends beyond the region we call the beginning. Causality still matters, and the block does not erase it, despite the fear that it might.
Light cones still separate what can be influenced from what cannot, and that separation is absolute. The block universe is not fatalism by itself, because fatalism is about helplessness and prediction. The block is a claim about what exists, not a claim about what an embedded observer can calculate. Now we revisit the arrow of time, because it is the strongest objection from experience and the most emotionally persuasive. We feel time flowing, and we remember the past, not the future, as if memory itself were a compass. In a block picture, the arrow is not a marching present. The arrow is a pattern in the block, tied to entropy gradients and boundary conditions. Entropy is the count of microscopic configurations compatible with a macroscopic state, and that definition hides a vast combinatorial landscape. A neat deck of cards is one macrostate, with relatively few microstates. A shuffled deck is a macrostate with astronomically many microstates, and that numerical imbalance matters. The second law says entropy tends to increase along typical trajectories, because there are more ways to be disordered than ordered. That tendency creates records, and records are the machinery of memory. Low entropy states can imprint information into many degrees of freedom, while high entropy states erase those correlations. When a footprint forms in wet sand, it is a local decrease of order in one place, paired with a larger increase elsewhere. The environment pays the entropy bill, and the bill is what makes the record stable. Memory is a physical process that depends on irreversible amplification, not a magical archive. Brains, cameras, and fossils work because entropy increases and leaves stable traces, like chemical changes, neural reinforcement, or mineral replacement.
A camera sensor must dissipate heat to lock in an image. A neuron must spend metabolic energy to strengthen a synapse. A fossil forms because chemistry runs downhill in a particular direction, and the rock keeps the result. So we remember the past because the past is the direction of lower entropy, where correlations were simpler and could be amplified into durable records. The future is the direction where correlations have not yet formed into records, at least not in our neighborhood of the block. This does not require the future to be unreal. It only requires that the block contains an entropy gradient, and that observers ride along it like boats riding a slope. The cosmological initial conditions matter here, because the arrow is not explained by local physics alone. The early universe appears to have been in a remarkably low entropy state, especially in gravitational degrees of freedom. That statement surprises people because the early universe was hot and nearly uniform, which sounds messy. Yet gravitational entropy is low when matter is smooth, because gravity prefers clumping, structure, and black holes. That low gravitational entropy is part of the documentary's recurring hook, and it is not a minor detail. If the Big Bang was the beginning of everything, why does the universe look like it remembers something? Why do we see a clean thermodynamic arrow rather than a symmetric blur?
The puzzle is not that entropy increases. The puzzle is why it started so low. In the block view, the memory is not a message from before time, and it is not evidence of a prior chapter written in secret. It is the consequence of a special boundary condition in a region of space-time, a constraint that makes one direction thermodynamically distinct. The arrow of time becomes a feature of the block's geometry and state, not a separate flowing substance. The block contains asymmetry, and we experience it as flow because our cognition is built to exploit that asymmetry. Now the scientific details tighten the picture, because the chapter's claim must rest on more than mood.
Space-time intervals give invariant structure, and invariants are what physics trusts.
Light cones give causal structure, and causal structure is what keeps the universe from becoming a contradiction. Foliations give observer-dependent nows, and that dependence is exactly what undermines a universal present. Relativity naturally fits a block because it treats time as a dimension, and dimensions do not need to move.
It does not privilege a global present, and it encodes physics in four-dimensional laws that look simplest when written without a preferred slicing.
Even in general relativity, where space-time can curve and where gravity is geometry, the block idea persists. A solution is a four-dimensional space-time, not a film being played in a projector. We often talk as if the universe evolves, because that language matches our computations and our lived sequence.
We set initial conditions, we run equations forward, and we watch graphs change. But the equations describe a whole space-time geometry satisfying constraints, and that geometry includes what we call past and future. The sense of evolution is partly a way of navigating the solution, not necessarily a feature of the solution itself. This is why the block universe feels like a trap, and why it belongs in a documentary with a mysterious tone.
It matches the formalism too well, and it makes the present feel like a local viewpoint rather than the universe's center.
It suggests that our privileged sense of now is like the horizon in a desert, real to the traveler, but not a boundary in the land. Now we confront the terror angle directly, because this chapter is the climax and it cannot hide behind abstraction. If all moments exist, then suffering is not something the universe leaves behind.
In the block, catastrophes are not erased by time's passage. They remain as real as any joy, fixed as regions of space-time with their own coordinates. The phrase, "it's over," becomes a statement inside a world line, not a statement about existence. Over means you moved past it, not that it stopped being. In a visual, we might see a city street after a disaster dissolve into a clean space-time grid, each tragedy pinned to a coordinate, unblinking.
The block does not soften its edges for our psychology. It simply contains.
This is terrifying because it attacks our deepest coping mechanism, and it does so with indifferent mathematics. We survive by believing the past is gone and the future is open, and the block questions both. Yet we must be careful not to smuggle in a false conclusion. The block does not say you are forced to feel every moment forever. It says the moments exist, whether or not you are there to witness them.
Your consciousness is localized along your world line, and that localization is crucial. You do not occupy the whole block at once, even if the block contains your whole history. Experience is not spread across the manifold like fog. Experience is a sequence of physical states in a brain, and those states are arranged along a time-like path. Still, the geometry is indifferent to comfort, and it makes no promise that reality aligns with narrative.
The block makes no promise that existence is a sequence with escape routes, and that is why it feels like a climax rather than a footnote.
It forces a question that is almost impolite. If the universe does not delete anything, what does healing mean in ontological terms? Is healing a change in what exists, or a change in where you stand within what exists? Now the chapter turns to the hardest complication, because the block is not the end of the argument.
Quantum mechanics seems to reintroduce openness because outcomes are not fixed until measurement, at least in some views.
Does quantum indeterminacy threaten the block universe? If the future is not determined, can it already exist in the same way as the past? The answer depends on interpretation, and this is where certainty dissolves into competing ontologies. Quantum theory predicts probabilities with extraordinary accuracy, from atomic spectra to semiconductor behavior. But it does not uniquely tell us what is real, and it does not force a single story about measurement. The formalism is clear, the meaning is not. In collapse interpretations, the wave function's evolution includes genuine stochastic events, and randomness is not just ignorance. The future is not fully real until a collapse selects an outcome, and that selection is a physical process. That picture clashes with a strict block, because the block would need to include a single definite future. Collapse makes the future partly undefined until it happens, and happens reintroduces the very becoming the block tries to avoid. In many worlds there is no collapse, only unitary evolution under the Schrödinger equation. All outcomes occur in a branching structure, and the universal wave function contains them as components. Many worlds can be seen as block-like in a larger sense, because the full structure is fixed by the dynamics. The future exists as a superposition of branches, and observers experience one branch as their history. In that framing, the block becomes bigger and stranger, and the terror changes shape rather than disappearing. It is not one fixed future, but a structure containing many consistent futures, all equally real in the theory. The now of an observer becomes the point where their branches' records are consistent. The feeling of choice becomes the experience of being located in one branch rather than another. Other approaches, like Bohmian mechanics, add hidden variables with deterministic trajectories, and they can preserve a fixed underlying history. They often do so with extra structure, like a guiding equation and a preferred configuration space. The cost is similar to the cost of a preferred frame in relativity. You can restore a certain kind of definiteness, but you pay with additional assumptions. Quantum gravity complicates the picture further, because time itself may be emergent in some approaches. If time is emergent, then the block might be a derived concept, not fundamental, and the deepest level might not be space-time at all. Some formulations even suggest a timeless equation, where dynamics appears only after you choose an internal clock. Yet relativity's lesson remains, and it remains stubborn. Any theory that respects Lorentz symmetry must confront the absence of a universal present, even if quantum rules are added. You can reinterpret what exists, you can enlarge the ontology, or you can hide a preferred structure. But you cannot easily resurrect a single global now without fighting the core symmetry that makes relativity work. So the block universe is not a fringe fantasy, and it is not just a philosopher's indulgence. It is a serious reading of space-time physics, and it survives many attempts to rescue a flowing now. It is also a lens that changes how cosmology feels, because cosmology is the story of the whole manifold. When you apply the lens, the Big Bang stops being a vanishing spark. Now we connect back to cosmology again, because the documentary's central question never leaves the frame. If the Big Bang is a region in space-time, then it did not vanish. In a block view, the early hot plasma still exists as a segment of the manifold. Recombination still exists, when electrons and nuclei first formed neutral atoms and the universe became transparent. The first stars still exist, igniting in dark halos and seeding heavier elements. The far future still exists, whether it is a cold thinning, a rip, or something stranger. The universe does not become older in an absolute sense, even if our calendars insist on it. We move along our world lines, and our local entropy gradient makes that motion feel like becoming. The ticking is real as a physical process in our bodies and devices. The metaphysical interpretation of ticking is what changes. The block reframing changes what before the Big Bang can mean. If time is part of the block, then before is only meaningful where space-time extends, and that is a subtle constraint. If the Big Bang is a boundary of space-time in a model, then there is no earlier region in that model. Asking what existed before becomes like asking what lies beyond the boundary of a map that has no ink there.
The question may be meaningful in a deeper theory, but the current model cannot answer it. But if the Big Bang is not a true boundary in a deeper theory, then there can be a larger block.
Our hot beginning would be a surface inside a bigger structure, perhaps a transition rather than an absolute edge.
Either way, the block picture makes the Big Bang less like a first tick and more like a coordinate landmark. It is a frontier in our description, not necessarily the start of existence. Now we revisit the documentary hook in its sharpest form, because it has been sharpened by everything we have built. If the Big Bang was the beginning of everything, why does the universe look like it remembers something? In this chapter, the answer becomes unsettlingly simple. The universe does not remember in the way a mind remembers. The universe contains, and we interpret patterns as memory from inside. The CMB and large-scale structure are still the evidence, but their meaning shifts under this lens. They are not echoes traveling from a vanished past like sound in a canyon.
They are features of a region,
and we are located where those features are visible. The microwave background is a surface of last scattering in space-time, and our telescopes intersect it along our past light cone. We call it ancient because of where it sits relative to us, not because it is fading out of existence. The block universe also reframes explanation, and this is where the tone becomes quietly alien.
Instead of asking what caused the present,
We can ask what global constraints define the whole space-time. That move is powerful and disturbing because it trades a story of becoming for a story of consistency. The universe becomes a fixed object with internal correlations, and we are patterns inside it trying to narrate it. Now we state the terror cleanly, because this is the climax chapter, and it must not flinch. If all moments exist, then there is no ultimate erasure, only different locations in time. The end of the universe, whatever it is not a future that might happen. It is a region that exists in the same ontological sense, even if we never reach it. That makes hope feel like a coordinate choice, and it makes regret feel like a coordinate choice, though the feelings are still real. It makes salvation feel like a perspective inside geometry, and that word inside matters.
From within a world line, the future is unknown, and the past is fixed in memory.
From the block perspective, both are simply there, and our ignorance is a local condition. Yet the block does not eliminate mystery, and it does not eliminate the central question. It changes what before means, but it does not tell us why the block exists. If space-time is the fundamental structure, we can still ask why this structure exists rather than none.
If space-time is emergent, we can ask what it emerges from,
and why that deeper layer has the shape it does. This is where the chapter must turn toward the finale, because the documentary's arc demands one last door. If time and reality can be reinterpreted as structure, what if the deepest layer is not matter or space-time at all? What if the deepest layer is mathematics itself, and the universe is one solution among many?
That possibility is the final chapter's door, and it is not comforting, because it suggests existence might be a property of consistency rather than creation.
We end on the transition that follows from everything we have built, and we let it hang in the air. If now is not a place, then reality might be defined by structure, not by experience. Next, we ask the last theory, because the block universe leaves one final question.
If the universe is a structure, what is it made of, and why does it exist?
We carry the central question forward, now sharpened into something almost inhuman. Did anything exist before the Big Bang? And if time began there, what could before even mean? The Big Bang may not be a first moment, but a frontier. The frontier may be where time stops being a flow and becomes a static fact. And if that is true, then the terrifying part is not that we are temporary.
The terrifying part is that nothing is ever truly gone,
and the universe does not blink.
Chapter 6 left us with a block of space-time that does not flow.
Now we take the final step and ask what the block is made of.
The camera drifts over a frozen lattice of galaxies, filaments and voids held in a single, unmoving geometry. We return to the central question with the last grammar change. Did anything exist before the Big Bang? And if time began there, what could before even mean? This chapter introduces the premise carefully, because it can sound like a trick.
The claim is not that numbers cause reality, as if equations were magical spells. The claim is quieter and stranger, that reality is a structure, and we are patterns inside it. To feel the weight of that idea, start with the oldest split in the philosophy of science. Is mathematics invented as a human language, or discovered as an external truth? Plato imagined an abstract realm of forms, while later thinkers treated math as a tool shaped by minds. If math is invented, physics is a translation layer we built for survival, tuned to our senses and our scale. If math is discovered, physics may be reading a pre-existing code, the way a radio reads a signal that was always there. Either way, the unreasonable effectiveness problem remains a hard fact, and it refuses to go away. Abstract equations predict real phenomena with precision, often before observation, and often in regimes nobody evolved to imagine. The success is not just qualitative, like a story that feels right. It is quantitative. Digits lining up in experiments, error bars shrinking, predictions surviving new instruments. Maxwell's equations did not merely fit electricity and magnetism, which were once separate sciences with separate vocabularies. They implied radio waves as a necessary consequence of changing fields, and the world later confirmed the implication with antennas, sparks, and distant voices. In visual terms, we watch invisible ripples leave a charge, then spread outward as a perfectly shaped wavefront. General relativity began as geometry and symmetry, written in tensor language that looks more like pure math than engineering. It predicted light bending near the sun, gravitational waves from orbiting masses, and black holes as stable solutions long before instruments could see them. On-screen, starlight arcs around a dark disk, and space-time grids sink like fabric under a heavy sphere, an analogy that is wrong yet still useful. Quantum theory began as an algebra of amplitudes, where probabilities come from complex numbers and interference patterns. It predicted spectral lines, tunneling through barriers, and entanglement correlations that still feel alien to everyday intuition. A particle appears as a smear of possibility, then snaps into a detector click. An event that looks simple but hides a precise mathematical rule. So we ask why math works this well, across scales and across domains, from atomic clocks to galaxy surveys. The final theory says it works because it is what exists, and everything else is interpretation layered on top. That is a radical sentence, so we slow down and place it on solid ground. Introduce mathematical realism in its modern form without overselling it. The view says mathematical objects exist independently of minds, even if no one ever writes them down. A prime number does not wait for a human to discover it, and a geometric relation does not depend on a language to be true. Then introduce Tegmark's mathematical universe hypothesis as the extreme version, where the step from realism to ontology is completed. The physical world is a mathematical structure, not a thing described by one. In MUH, the universe is not made of substance with equations painted on later. The universe is the equations, fully specified, internally consistent, and complete in the way a structure can be complete. In MUH, existence is not made of matter or energy as fundamental stuff. Existence equals mathematical consistency, and physicality is just being inside the structure as one of its self-consistent sub-patterns. We do not float above it as observers. We are part of the formal object, like a theorem is part of a proof. That sounds like wordplay, until the key move is stated clearly and held in view. A structure does not begin in time, because time is a relation inside it. You do not ask when a triangle started existing, because when presumes a clock that the triangle itself does not contain. In this framework, before the Big Bang,
is not a hidden era behind a curtain.
It is a category error, like asking for a page number before the book. The Big Bang becomes a coordinate boundary inside the object we call space-time, a limit where our familiar chart stops working. Our charts end at a limit, while the structure simply is, the way a coastline exists even where a map fades into blank paper. Time, in this view, is not a river outside the equations pushing moments forward.
Time is an ordering relation defined by the structure's internal geometry, the way earlier and later are defined by paths through space-time.
So the question shifts from what happened earlier to what the full structure contains. The Big Bang is a feature of our slice through it, like a horizon line that depends on where you stand. When cosmologists talk about a singularity, they often mean a breakdown of classical description, not necessarily an actual point of infinite density.
Now connect this to the documentary's hook about cosmic memory.
If the Big Bang was the beginning of everything, why does the universe look like it remembers? We see patterns that behave like traces, fossil photons, element ratios, and correlations stretched across the sky. Yet memory usually implies a past that left a mark, and that is exactly what know before seems to deny. In a mathematical universe, memory is not a message from a prior time outside the structure.
It is an internal correlation pattern that our location makes visible, because we occupy a region where those correlations are accessible.
The universe does not recall. It simply contains relations that look from inside like evidence. The CMB's smoothness and its tiny anisotropies become structural facts. They are constraints satisfied by the solution we inhabit, like boundary conditions that select one consistent pattern out of many.
On screen, the microwave sky becomes a mottled sphere, with subtle temperature speckles that encode early density variations.
Those speckles are not random noise. They are statistically describable, with power spectra that match simple inflationary models. Even in this chapter, where we are careful not to change topics, that statistical regularity matters. It shows how deep structure can appear as a faint texture in a cosmic photograph.
The same is true for nucleosynthesis and the thermal history.
The light elements are not just remnants, they are consistency conditions. Given expansion, particle physics, and reaction rates, the early universe must synthesize helium and deuterium in narrow ranges, and observations land close to those ranges. Now pivot to information language, because it often shadows this idea. Many physicists describe laws as algorithms and states as bit patterns, partly because prediction is compression.
If you can summarize 1 trillion measurements with a short equation, you have extracted structure from data.
Information talk can be a metaphor for compressibility and prediction, and it is powerful in that modest role. It can also be a claim that the universe is computation, literally running like software on some deeper hardware. The chapter keeps the distinction sharp, because confusing metaphor with ontology is how mysteries become slogans.
State the careful distinction that keeps this chapter honest.
Computation can be a useful model, but not every model is literal ontology. A weather simulation is not made of clouds, and a differential equation is not automatically a machine. Still, the information angle fits the structural theme, because physical states can be encoded, transformed, and constrained like data in a program. In that framing, laws are update rules, and dynamics is computation over a state space.
Time becomes the indexing of those transformations, a bookkeeping label for successive relations.
If you zoom into a quantum field, the state is not a list of particle positions. It is a vector in a Hilbert space, evolving by a rule that preserves probabilities. That language already feels like mathematics first, physics second, which is why Moog can seem less like a leap and more like a completion. But testability matters, so we ask what changes if this is true.
If it predicts nothing new,
It risks being only a relabeling, an elegant restatement with no empirical bite. A philosophy can be internally coherent and still fail as a scientific guide. Now we ground the chapter in modern physics, where structure already dominates. Symmetry principles often come before particles in our best theories,
and the particles arrive as representations of those symmetries. In other words, the rules of transformation can be more fundamental than the things that transform. Noether's theorem is the clean bridge from symmetry to reality. Continuous symmetries imply conservation laws, and the universe obeys them relentlessly. When the equations do not change under a shift, a quantity remains constant. And that is not poetry. It is a theorem with a precise proof. Energy conservation follows from time translation symmetry in the right settings, meaning the laws look the same tomorrow as they do today. Momentum conservation follows from spatial translation symmetry, meaning the laws do not care where you stand. Angular momentum conservation follows from rotational symmetry, meaning the laws do not care which way you face. These are not optional features, they are the skeleton of physical explanation. They are also hints that the universe is built from invariances, from what remains unchanged under transformation. On screen, rotating coordinate axes leave the same equations glowing in place, while physical trajectories keep their conserved quantities like a signature. Gauge symmetry does similar work in quantum field theory. It constrains interactions so tightly that forces look like geometric necessities, emerging from the demand that certain transformations change nothing observable. Electromagnetism arises from a simple symmetry of phase, and the math leaves little room for improvisation. General relativity goes further by turning gravity into geometry. Matter tells space-time how to curve, and curvature tells matter how to move. The famous phrase is memorable because it is accurate, and because it flips the old mechanical picture into a structural one. So physics increasingly resembles constraint satisfaction inside a mathematical space.
The world looks less like machinery and more like a solution, a consistent configuration that satisfies deep invariances. When we solve field equations, we are not assembling parts, we are identifying allowed patterns. Now tie back to earlier chapters because this is the finale and it must gather threads. Each prior theory can be reframed as a structural choice, a different way the full mathematical object might contain our observable slice. The earlier options were not wasted detours. They were glimpses of how beginning can dissolve under different formalisms. The cyclic universe becomes a repeating pattern in a mathematical object. The bounce is not a first cause. It is a feature of the solution, like a periodic boundary condition that produces recurrence. Visually, the scale factor rises and falls as a smooth waveform, not as a story with a first chapter.
Quantum nothing becomes the absence of classical spacetime, not the absence of structure. The no-boundary idea becomes a geometric condition, where time behaves like a spatial dimension near the limit, smoothing what would otherwise be a sharp edge. The picture is a rounded cap rather than a corner, a manifold without a boundary you can point to. Vilenkin tunneling becomes a rule for weighting histories, not a literal popping into being like a firework in empty space. The hard question becomes why that rule and measure, because the rule is itself part of the structure. The math can generate probabilities, but probabilities still require a framework that tells you what counts as a possibility. Eternal inflation becomes endless production inside a larger mathematical landscape. The measure problem becomes a problem of counting within structure, because how many depends on how you define the counting. Even in a purely mathematical multiverse, the act of assigning typicality is a technical choice, not a free gift. Brain collisions become higher dimensional geometry intersecting our slice. The Big Bang becomes a boundary where coordinates change their meaning, the way a chart fails at a pole even though the sphere continues. On screen, two vast membranes drift and touch, and a bright seam marks the intersection that we interpret as a beginning. No beginning becomes the claim that the structure has no earliest time relation. The block universe becomes the claim that the structure is already whole, with every event laid out as part of a four-dimensional object. In that view, becoming is a feature of consciousness, not a feature of the underlying geometry. Now we reveal the terrifying implication that makes this chapter the final edge. If existence equals consistency, then all consistent structures exist. That is the ultimate multiverse, not of bubbles in space, but of all possible equations, all possible axioms, all possible internally coherent rule sets. Our universe becomes one point in an infinite library, a single volume among uncountably many. The camera moves through endless shelves of abstract forms, some simple, some baroque, some with familiar symmetries, others with laws so strange they resist visualization. In that library, every set of laws that does not contradict itself is real.
Every history that can be encoded exists somewhere in the abstract totality, whether or not it contains stars, chemistry, or minds. The terror is not only that we are not central. The terror is that reality may be too large for meaning to anchor itself. If all structures exist, then why this universe becomes a selection problem. We must explain why we observe these laws and not others, and why our observations fall in a narrow band that permits stable complexity.
That forces the discussion into typicality and measure, which earlier chapters already touched.
Without a measure, prediction collapses into enumeration. If everything exists, then saying, somewhere this happens, becomes trivial, and science demands more than triviality. We need a way to say what observers should expect to see, given that they exist at all. So we ask what would count as evidence for MUH, or mathematical realism.
Direct proof is unlikely because the claim sits behind all observations, like the paper behind every printed word.
Yet frameworks can still guide expectations, and guidance can be tested indirectly. They can favor simplicity, compressibility, and symmetry as signs of typical observers in typical structures. They can also suggest that our laws should be algorithmically simple, because simple structures are more numerous under many counting schemes.
That is a subtle argument.
And it depends on how you define more numerous in an infinite space. Yet counting schemes are themselves assumptions, and the chapter must not hide that. A measure over structures is not given by logic alone, and different measures can yield different notions of typicality. The mathematics does not automatically tell you which weighting is the correct one for prediction. This is where falsifiability becomes the central tension.
If every consistent universe exists,
then any observation is compatible with something, somewhere in the library. The response is that compatibility is not prediction, and prediction is what science trades in. A good framework must say what we should expect to see, not merely allow it. It must compress experience into a small set of high-probability outcomes, and it must risk being wrong. Otherwise, it becomes a mirror that reflects whatever we already know.
So we return to the practical tests earlier chapters promised.
Curvature constraints, primordial gravitational waves, and larger-scale CMB anomalies still matter. They do not prove MUH directly, but they probe whether our observed slice fits simple boundary conditions or requires special pleading. If the Big Bang is a coordinate boundary inside a deeper structure, subtle signatures might survive.
They could appear as non-trivial topology, like matched circles in the microwave sky,
or as unusual correlations that do not fade with distance. Even a small deviation from statistical isotropy would be a clue that our map is missing a global feature. If quantum creation proposals are boundary conditions, they might bias curvature or tensor modes. Hartle, Hawking, and Vilenkin can imply different likelihoods, not as metaphysical preferences, but as calculable weightings. In principle, improved polarization maps of the CMB could tighten those weightings, forcing some boundary choices into tension. But the deeper worry remains, and it is part of the horror. Even the boundary conditions assume a Hilbert space, a law, and a measure. In a mathematical universe, those assumptions are not external choices made by a theorist. They are parts of the structure, and we still ask why that structure exists rather than another.
Now the chapter turns the hook into its final form.
If the universe looks like it remembers something, maybe it remembers nothing at all. Maybe the memory is simply that we are inside a rigid pattern that includes our observations, our instruments, and our questions. The clues are not messages, they are coordinates. The CMB is not a postcard from a vanished time outside the structure.
It is a surface of last scattering inside the structure.
a relation between matter and radiation that our location lets us see. So the Big Bang may be less an event and more a limit of our description. Our map ends at a boundary, not necessarily the territory. That boundary can be a singularity in classical equations, a quantum transition, a bounce or a collision. In this chapter, it can also be a coordinate edge, the place where earlier stops being well-defined.
Now we answer the central question in the only way this theory allows. Did anything exist before the Big Bang depends on what before means. If time is internal to the structure, then there was never a before. The structure does not start. It simply is mathematically. If we insist on before, we are importing human intuition about cause and sequence. We are asking the universe to speak our grammar, and then we are surprised when the sentence fails. The failure is not necessarily in the universe. The failure may be in the question. The finale must land on the documentary's conclusion theme, because every chapter pointed here. The Big Bang may not be a first moment, but a frontier, a boundary of applicability where our familiar concepts become unreliable. Previous universe, quantum nothing, infinite factory, brain collision, no beginning, and block time all point to the same pressure. Our intuition fails at the boundary, because intuition was trained on mid-sized objects moving slowly in a stable environment. Mathematics is the last and strangest option, because it removes the boundary from time itself. It makes existence a property of consistency, and it makes beginning a feature of perspective. So we close on the question that remains when before dissolves. If reality is mathematics, why do we find ourselves in this equation? And if every consistent equation exists, then terror is not emptiness. Terror is infinity, and the possibility that meaning is only local. We end where the map runs out, and we do not pretend the territory ends. The Big Bang is a frontier, and beyond it may be pure structure. The final thought is simple and unsettling. Maybe before is not real, and the universe's true shape is mathematics. Across these 7 theories, the Big Bang stopped looking like a first page and started looking like a border, the place where our usual rules lose their grip. We followed hints of a previous universe fading into ours, a quantum nothing that is never truly lawless, an infinite factory of bubble births, and even a brain collision that turns creation into impact. Then we press deeper, toward time with no first moment, a block where every moment still exists, and finally the unsettling possibility